Good afternoon, everyone. Am I audible?
Yes, and you are audible.
Okay. So welcome everybody to this revision session for the topics starting from week 9 up to week 12. So this should help you prepare for your final exam day after tomorrow. Okay. Nitin, would you like to start?
Yes, and sure. So, good afternoon, everyone. So, should we start or wait for someone else to join?
Okay, sure. Let's wait for a few minutes. Yeah.
Yes, sir. Okay. So, I think we should start now.
Sure, Nitin.
Is my screen visible?
Yes, it's.
Okay. So, give me 1 minute. Okay. So, good afternoon, everyone. In this session, we are going to revise week 9, 10, 11, and 12 for the upcoming exams. And other weeks we have already revised in the quizzes. So here we are considering only week 9 to 12. So let us start with week 9. Week 9 is decision tree. Okay. Okay. So let us start with week 9. Decision trees are supervised learning algorithm. It means that each and every example are associated with its labels, and they are non-parametric. It means that we don't assume we don't make any assumptions about the distribution of the dataset as before we have done for other algorithms. But decision trees are non-parametric. And decision tree can be used for both modeling for both classification and regression tasks. So what are decision trees? Let's move to that. So decision trees are nothing but we partition our input space or feature space into the different sets of rectangles and we model a constant in those rectangles. What I mean by modeling a constant, remember in the case of regression, in each leaf node we model that the prediction will be the mean of all the labels belonging to that particular node. Or in the case of classification, we predict the class that majority of examples belongs to that class. We predict the class to that node. Right, so that's what we mean by modeling a constant in the rectangular regions. So let's move ahead. So this is one particular example how decision trees typically look like. So this example consists of the 14 samples and 4 features. Features are outlook, wind, temperature, and outlook, humidity, wind, and temperature. Now, and the label is play whether according to these features, whether it particular sports, I think tennis should be played or not. So it's a binary classification problem here. And remember here in this case, all the features are categorical as well. So how to make, so for this particular examples, a particular decision tree may look like something like that. So how to make such, how to train this decision tree. So this will be our task in this session. So our questions will be which attributes to choose for splitting, right? For the root node for our entire in this particular example, for the entire data set, we have split according to the feature outlook, and then their child node have been split according to different attributes. Like this child node have been split using the attribute humidity, and the right child have been split according to attributes wind. So which attributes to choose at which level, and what will be the splitting criteria for different at different levels, and what will be the tree size that will give the optimal solutions? Should we go for the full last tree, or should we split? Should we not go to the last tree? So this kind of questions we will answer in the upcoming slides, in the next slides. So there are some different algorithms for decision trees. The first algorithm is which is ID3, and the remaining algorithm like C4.5 and TART. All these are the variations of ID3 algorithm. So let's move to the ID3 first. So as usual, data are the X is the matrix of size n cross m, where m are the number of features and n are the number of examples. And this particular is the ith example, and so it is a vector of size n. And this is the label associated with the ith example. And we have such n examples, and so X will be the matrix of size n cross m, and their associate level will be by 1, by 2, up to in. So this is how our data is looking like. And the by here in the classification problem, it's gonna be discrete values, and in the regression, it's gonna be a real number. So so let's move to the ID3. So ID3 employs top-down. Let's start with the entire data set and then split from top to down in the greedy search manner. What I mean by greedy search manner, it means that at a particular step, at a particular iterations, it only takes the best attribute to split at that moment only. It doesn't consider what will happen to the next split, next iteration, and the next iterations. It only takes care of at the particular iteration, at the particular moment, what will be the best attributes looking at the examples belonging to that node. So that's in that manner, it's a greedy search algorithm. And so our question is at which node and at a particular node, which attributes to choose to split the data set. For that, we will define some impurity measures to split our data set. Okay, so this is one example of the classification problem where there are two features x1 and x2, and both are the numerical features. So if we divide along with the entire data set, and this is belongs to two classes, red and blue classes. So this is how our data are distributed. So if you look at, we have to split this data set into the regions according to features x1 and x2. So assume we have split our data set according to features x1 such that if x1 is less than theta1, then we are calling the right node to be, or say the region belonging left region to be R1 and the right region to be R2. So all these examples here will belongs to the region R1, and all these examples belongs to the region R2. Again, we can split this data set as well, because remember, because in this node again there are distribution of both classes red and blue. So if we split the region R1 according to feature X2, such that if X2 is less than theta2 or greater than theta2, it will split into the regions R3. This is R3 and R4. Now look at R3. Now all the examples belonging to R3 belongs to a particular class, that is blue class. So we need not to split R2 again. Similarly for R4, we need not to split this one. But R2 we can again split it. If we again split R2 according to the feature X2, such that if it is less than theta3, and so it will split into two regions, R5 and R6. Similarly, in the manner we can split our data set, and this is one of the trees we can get from this data set, right? It can again split further, because remember in R8 and R7 is not pure nodes here. Pure nodes means there are examples belonging to only one class. But here you can see different both the classes, example from both the classes are present here. So we can again split it, but this gonna be overfit our data set that we will talk about later. So this is how a typical decision tree looks like for this particular data set. Okay, so we were talking about the ID algorithm. So one assumption that ID3 makes that in ID3 algorithm, the features is always categorical features, and this is the one of the restrictions that we make about the ID3, and that's why it restricted its use for different algorithms, and we make different variations of ID3, and one of these is cart as well. We will see that here. For training of any decision tree, these are the steps we follow. First, we take entire data set and we split the that data set according to the attributes. So which attributes to choose, that we will see now. So best attribute is selected to use for splitting the root node. Root node means the entire data set, and once it is splitted, their descendants, or say child nodes, again same procedure is repeated for their child nodes up to where we can get the pure nodes, or we cannot get further splitting for those nodes. So this is our training process for any decision tree. And ID3 never backtracks. Once we have learned a full decision tree. Full decision tree means there's no further splitting. It never backtracks. This is one of the features, one of the, you can say, limitations of ID3 as well. How to choose the best attribute? This is our one questions that we need to answer. So how to choose best attributes? For there we will define some measures. Before defining the measures, there is one notion which actually gives you the proportion of data points belonging to different nodes. So here PIK means I stands for the ith node, K stands for the class. So PIK means that the proportion of the data set belongs to the class K in the node I. So this is the proportion of those class data sets. So how you will calculate this? This is the indicator function. So it will look for those example in region Ri for which the label is K, right? Otherwise it will be 0. So it will count all those numbers which belong, all the numbers of those data points which belongs to class K, and Ni is the total number of the data points in that node I. So this will give you the proportion of data points in node I which belongs to the class K. For every such K, we can calculate the proportions, and this is the notion we will use for defining our different measures. One of the measures is misclassification error. So as the name suggests, misclassification error is the proportion of misclassified examples. So this gonna be how to make the predictions that in the node, in the leaf nodes. So in the classification problem, remember the majority of, in the particular node, the majority of class we will predict the majority of class node, right? So PIK will be the proportions. We will look for such K where the PIK is maximum. So it will give the class where the majority class data points belong to that class. So we will predict that class in that particular node So what will be the proportion of misclassified example? That it's gonna be 1 minus PIK. So because remember that it's proportion, so overall proportion is gonna be 1. So 1 minus PIK will give you the proportion of misclassified examples. So this is one of the misclassification error measure. Next is gain index. So it is defined as sum over PIK 1 minus PIK. So sum over all such classes. So we will find the proportion for such all such classes, and we take the summation of PIK 1 minus PIK. So this is gain index. So gain index actually gives you the captures the randomness or say degree of inequalities in that node. Remember, if there are only two classes, PIK 1 minus PIK gonna be your variance. So you can think this expression as you can think as we can each observation as 1 and all other observation as 0. Then it is gonna be the variance, and we will sum over all such classes. So actually, gain index captures the degree of inequality in that particular node. And if you look at this equation, you can say that the maximum value of gain index is 0.5. And if the 0.5, the value of gain index will be 0.5 only when there are equal numbers of data, equal proportion of data for all classes. Let's say there are two classes in the 1:1, that is equal proportion. Then the gain index of that node will be 0.5. That is the maximum gain index. And the lower in gain index means there's less randomness in the data set, distribution of the data set. So 0 means the node is pure. That is the sample belongs to only the one class to that node. Okay, so that's how gain index goes from 0 to 0.5. Another is the entropy. It again captures the randomness in the data set. It is defined as PIK log 2 PIK sum over all such classes. And the maximum value of entropy is gonna be 1. Higher value of entropy denotes the higher randomness in the data set. So entropy 1 means that there the equal proportion of data set. Equal proportion of the different classes belongs to that particular node, and 0 means on pure node. So we want the entropy to be minimize the entropy to split our data set, right? And another measure we define as the information gain. So it is defined as the reduction in the entropy, right? So once the reduction is made, once the split is made, how much entropy has been reduced from the data set, and after the split, what is the entropy? So that reduction is called the information gain, and we want information gain to be higher because higher information gain means higher reduction in the entropy, and reduction we want higher because entropy we want to minimize, right? So that's these are the three measures we choose for splitting for finding the splitting variable or say attributes along which we have to split our data set. Yeah, here one point I want to make that if it is nothing is mentioned about which measure to use. If information gain means we have to use the measure and entropy as a measure. But if it is mentioned that if we are splitting our data set using gain index, then information can also be defined using gain index as well. Okay, both measures can be used for information gain. So this is the example. This is the entropy of the data set, and after the splitting, we will find the entropy for the child nodes, and we take the weighted sum. So that is going to be the entropy after the split. So the reduction will be the difference of these. So this is how we define the information gain. And we choose the attributes to split for which there is largest information gain. Right.
So this information gain is related to entropy, right? What you said, I think, like what I heard is like you can also calculate information gain from gain index, right?
Yeah, if it has nothing mentioned and nothing, no other context is given, then information gain is the reduction in the gross entropy. But if you are splitting your data set as per gain index, then information gain you can also calculate using gain index. That in that case, it is gonna be the reduction in the gain index. Is it clear?
No, so you are saying that is equivalent, right? Or you are saying information gain equal to the original Gini index minus the new one
Newman means after the split.
after the split. Okay.
Yeah. So where this training stops, where the recursion of splitting stops, once we get all the nodes as pure nodes. Is anyone saying something?
Yes, sir. I have one question regarding if we have a unique features, like all the feature data points are unique, and if features have means the number of occurrences are not unique, do we have any means just means understanding like how we can calculate the entropy? Means okay, the formula remains same, but just trying to have a generic view. Means if the complete.
So what do you mean by all the features are unique?
Means all the distinct, right? The features, like if you say, wind is weak, strong, and there are only two inputs for the features. And if we take a kind of normal any other features like where have all the entries have a unique entries, all the entries have
okay. So you mean if the features are numerical or categorical? In the case of categorical, we can define like.
Oh yes, it's a numerical in range, right.
Yeah. So categorical, then we can split according to whether wind, whether that wind is weak or strong, something the temperature is high, normal, or something like that, right? But in the case of numerical, we can define split like x1 is less than some point, or x1 is greater than, let's say x1 is your feature, numerical feature. So you can make splits according to x1 is less than some value, or x1 greater than some value. In that case, you will always get binary split. That is, it will split into two child nodes, right?
So
and those values.
Yeah. So in case of calculating entropy, probably the question should have that S value to the split value, right? We'll always have that.
No. Entropy is calculated using proportions, using labels. Let's say, just forget about whether these attributes are categorical or numerical. Once you make a split, you will check the labels there. Let's say in the child node, these first five examples, just 4 examples, these 5 examples belongs to one particular node.
No, just take the day and play. Day is the feature and play is your label.
No, day is not a feature here.
No, I'm just taking an example. If this is all unique, right? D1, D1, D2, D3, D4, all are unique values. For whatever, you can take it numerical also. Instead of D1, it will 1, 2, 3, 4, 5, 6 to 14.
Yeah, let's say temperature is a numerical feature here, and temperature values are given. Let's say some 20 degree, 25 degree,
correct,
like that. And you have make a split according to temperature, something like temperature is less than 25 and temperature is greater than 25. Okay, so now what you will have 2 child nodes, and those child nodes you will have some data set belonging to those 2 different child nodes, right? Now, how you will calculate the entropy for these child nodes? You will find the proportion of data set that belongs to different classes. Let's say these first 5 examples belonging to the left node. Okay, so the proportion will be 2 by 5, 3 by 5, right? So what will be the entropy? Minus 3 by 5 log 2 3 by 5 and plus minus 2 by 5 log 2 by 5. You are not making use of split value for calculating the entropy. You are making use of the proportions according to the labels. Labels are
that's correct.
So we are talking about the classification.
Right. So I see, that's what I'm saying. So we'll have to give the split value, right? Otherwise, we have to judge that split value. What would be the split value?
Yeah. That is one question. What split value to choose, right?
Yeah. What split
value to choose and what split value to choose? That we will consider in the next algorithm, where we will find what split value we need to choose. In the case of ID3, all the features should be categorical.
So
we will see that split value also we need to find.
So before calculating entropy, we'll have to find the split value, right?
Calculating entropy, we need to find a split.
So before going to calculate entropy, we have to identify the split value. What will be the split?
Okay, so once you have the data set, you can find entropy, right? You have data set belonging to a particular node, then you can find the entropy of that node.
Yeah, we can find the entropy of overall data set.
Yeah, overall data set.
But I'm asking for a particular temperature as a input feature.
I'm muting everyone, and Nishant, you can unmute yourself and then continue.
Okay, see what I'm saying, that we can calculate the entropy for complete data sets looking at the label, that we understood properly.
Yeah.
But if we have a feature that numerical in nature, and first we'll have to calculate the splitting point before going for calculating the entropy, right?
Yeah, obviously.
So okay, it means if the questions have those entropy, have the split value have to be given before going to calculate the.
Yeah. If in the question, if it's asked to find information gain or change in entropy, then split value obviously it will be given to you.
Okay.
To make the split.
That's what my confusion. Thank you so much.
Okay.
Yeah, so that's how even the OPP exams, right? The assignments were with that, questions were with that, they're given the split value. So you have to go with the split value.
Okay.
Yeah, okay. So let's continue here. So we were talking about the information gain, and so let's look at one example to make all the things clear. So the same example we were talking about, 4 features, all categorical in the level, whether to play whatever sports or not. Okay, so here the data set consists of the 14 examples, where class no contains 5 examples, and the class yes contains the remaining 9 examples. Right. So the proportion should be 9 by 14, 15 by 14. So the entropy of the data set gonna be minus 9 by 14, log to 9 by 14. In similarly, it's gonna be 0.9 times. So look at this value; it is very high. It's close to 1. So it means that there are randomness in the data set. Right, because if 14 examples, so the mid value is 7, so 5 belongs to the class no, and 9 belongs to class yes, so you can say the higher randomness in the data set. Right? Now choose attributes. So we will how RDP works. It takes all the attributes and find the information in for all the possible attributes. For here we will find that for wind. So if we choose wind, then how we will make the split? We will make the split according to if it is weak or strong. If it is weak, then in the, let's say if it is weak, then the left node, and if it is strong, then it split into the right node. So in the leaf node, how many examples will be there? So weak, these examples where the wind is weak, all those examples will belong to the left node. So in those examples, so weak has total 8 examples, out of which 6 has label yes and 2 has label no. You can check from these here. So that particular node, left node, will have the entropy 6 by 8 log to 6 by 8 minus 2 by 8 log to 2 by 8. So this is gonna be entropy of the left node, and the right node will be correspond to wind equal to strong. In that case, so there will be 6 examples, 3 belongs to class yes and 3 belongs to class no. So the entropy of that right node gonna be 3 by 6 log to 3 by 6, and similarly it is gonna be 1. You can see 1 means that equal proportions, 3 yes, 3 no, right? So what is gonna be information gain here? So information gain gonna be entropy of the data set minus the weighted sum of those entropies that we have calculated. So it is entropy of data set was 0.94, and here the weights are the proportions of the examples in those nodes. Remember, in the weak left node there were 8 examples, and the right node there were 6 examples. So these gonna be the weights, and the entropies gonna be 0.8 and 0.04. So information gain gonna be 0.048 if we choose attributes as wind. Now let's check for other attributes as well. In the same way, we will find out the information gain for all remaining 3 features. Yes, information gain gonna be 0.048 for wind, for outlets gonna be 0.24, temperature 0.029, 0.15 for the humidity. So the maximum information gain is for the outlook. It means that we will split our data set according to the features outlook. So our data set will be split according to feature outlook. If it is sunny, then this node will have these 5 examples. Again, we can split this node in the similar manner, right? If it is overcast, then this example will belong to here. And look here, it is the pure nodes because all the examples will belong to the same class. So we need not to split it further. If the outlook is rain, so this particular node will again have the each 5 example, and we can again split this node in the same procedure with the same procedure. And your full tree gonna be look like this. Okay, so that's how we find a decision tree using ID3 algorithm. Okay, so next is classification and regression trees called CART in short. So this is the extended version of ID3 and C4.5. So CART uses both regression and classification problem as it stands classification and regression trees. It's very similar, but it's very similar to ID3, but here we can have both categorical and numerical features as well. So again, the same questions: which feature to use and which splitting value to find, right? So, and the prediction in the classification case, we have make the majority class, and in the case of regression, we make the prediction as the mean value of all the labels present in that particular node. Okay, so that is gonna be prediction in the case of regression problem. So there will be 2 questions: which parameter to choose and which split value to choose, right? And here prediction is CI, which actually means that you can verify as well. So for finding those, it makes the loss function. Loss function is once we have split our data set, so the actual level and the predicted levels, we will find the sum of squared error. And now we have to choose. Let's say we are using some jth features to split our data set. So it will split into the 2 nodes, R1 and R2. In the R1, those examples where x1 is less than s, and the right node will be all those in the right node. All example will be there where xj, that is jth features, is greater than s, right? So we have to find this s and this j, which feature and which split value we have to use. So for that, we will minimize this thing. We will minimize the sum of squared error in both the nodes. So remember, this gonna be this particular terminology is gonna be the loss or error in the right node, and this is gonna be loss in the left node, right? And we will minimize this error, and we will minimize over j and s. Such we will track all such j's, possible j's, and all possible s. Okay, for different choice of j and s, we can minimize this thing. And remember, this inner minimization is gonna be the mean of all those examples belonging to that node. So ci is gonna be your the mean, and then j and s, we will track over all such possible j and s to find such minima. Okay, that's how your and we always can find such pair for which that particular expression is minimum. All other training process goes in the similar manner. We will repeat again for the child nodes up to, till we stop our full grown decision tree. Different measures can be used. Variance reduction can be used rather than sum of squared error as well there. In the case of classification tree, remember here we have make use of sum of squared error. In the classification tree, we can make use of other measures like we have already defined misclassification error, gain index, and the entropy that we can make use of, and all the procedure goes in the similar manner. So these are 2 points about these measures. Cross entropy and green index are differentiable, but the obviously misclassification error is not differentiable. So these are the mostly used in the numerical optimizations. And again, cross entropy and green index are better measures because they are sensitive to node probabilities. What I mean by sensitive, if we change the node probabilities, then the change in misclassification rate will be higher rather than the cross entropy and green index. They will not change by much factor, but the misclassification error can be changed by the huge factor. That's why the cross entropy and green index are better measures. Yeah, okay. So okay, so up to here we have found how to make the full tree, how to split our data set, and how to find the best split point and how to find the best attributes to split. Right now, up to what point we size of it is defined as the longest path from the root node to the leaf. That is gonna be size of tree, and root node itself is considered to be of size 0. And the size of tree is a determining factor for overfitting and underfitting. Let's look how it's may overfit and underfit. So how it can overfit? Remember, in the decision tree, it is very flexible for partitioning the data set into the smaller regions. In that case, what will happen? That for the training example, it tries to place each and every example to the pure nodes. In that case, it will give the very less error for the training set, but for new unseen data, it may give higher data set. In that case, the decision tree can be overfit. Remember, it checks for each and every possible split point and each and every possible split variable. So it keep on growing till we get the full tree, and that tree can overfit as well. And if we don't grow the full tree and we stop somewhere else, and that tree might not capture the important feature, and in that case it may underfit as well. So tree size is the determining factor for overfitting and underfitting. And so how to overcome these problems? So there's two methods to avoid overfitting. One is called pre-pruning. Pre-pruning means it's just not to grow full tree. Rather than growing the full tree, we just stop the tree and we can specify some threshold for number of samples in the leaf nodes to stop our tree, or either we can stop expanding the tree if it doesn't make any much changes in the impurities. So this is gonna be stopping criteria for the pre-pruning. So next pruning is next method to avoid overfitting is called post-pruning, and one of the method is cost complexity method. So what happens in the cost complexity method? We grow a full size tree and then prune back. Prune back means we will remove some of the internal nodes and make those leaf nodes. And this is by what I mean by prune back. So how it works? We will first grow a full tree. Let's call it T node, and we are defining T to be a subtree for that T node. Okay, and we define that pruning criteria to be all the classification error for the leaf nodes and the alpha times number of leaf nodes. This mod of T is nothing but the complexity of the tree. So it is the number of leaf nodes in the tree. So it decides the complexity of the tree. Remember, if there are large number of leaf nodes, then the tree will be more complex. And this alpha is called complexity parameter or regularization parameter. So we want to prune in such a manner that this CT is minimized. So how to make sure that the CT will be minimized? So value of alpha takes care of this. So alpha is called complexity parameter. If you choose alpha to be 0, so remember, if we choose alpha to be 0 and we want to minimize this thing, so this is the error corresponding to all the leaf nodes. So if alpha is 0, then we want the tree to be large grown to minimize these things. Remember, because if we split our tree to the maximum up to the maximum depth, then in that case error will be lesser. right? So this term gonna be lesser. So alpha 0 means that we want to grow a last tree, and if alpha is infinity, then for minimizing city, we want the number of or the complexity of the tree, that is number of leaf nodes, to be lesser, because if we choose alpha to be infinity, this should be 0, and 0 means that there is no splitting of the data set. So alpha infinity means that we will not split our data set. So how to choose this alpha? Alpha takes care of for determining the subtrees. So this alpha is found out using the cross validation value. That's how cost complexity works for post-pruning. Okay, so this is all about how to avoid the overfitting in the decision tree. This is the advantage of the decision tree. Decision tree are very versatile. It means it can perform both classification and regression problem, and very easy to understand, interpret it, and it can be visualized as well. And decision trees requires very little data pre-processing. Remember, we haven't done any feature scaling. We need not to do any to take care of the missing values. We need not to add any dummy features as well. So we need very little data preprocessing in the case of decision trees. And cost of the decision tree is logarithmic in number of training data set, because it keeps on splitting each and every nodes, right, in two parts, more than two parts or two parts. And so some disadvantages are there. One of these is these are very prone to overfitting. Remember, it captures the noise as well. It fits our training data set very nicely, but it again learns the noise in the data set as well. So this is one of the advantages of the decision tree. It also again may have high variance just because it learns the noise in the data set, and we grow large data set, so it makes predictions on the fewer examples. In that case, the variance will be higher for decision trees. So this is the few disadvantages of the decision trees. And trees learns the piecewise linear approximation, and hence are not good at extrapolations. So these are some disadvantages of the decision trees. So this is all about the week 9. So if you have any doubts or concern, you can ask.
Yeah, can you go back to that pruning slide, because it was too fast actually.
Pruning, this one.
Yeah. This one. So this QT is the misclassification, right?
Yeah, QT is a misclassification for all those leaf nodes.
All those leaf nodes.
And this mod of T denotes the number of leaf nodes. So I is here running from 1 to T. So it takes the sum of all the misclassification error for that node, that tree.
No. So okay, let me understand. Say for example, you have a node that you want to prune. So it is an internal node, right?
No, we prune back means that we internal node, we make that a leaf node.
Correct. So basically you are pruning that particular node. When you are pruning an internal node, right?
Yes.
Okay. So that internal node, like remaining, like whatever the childs under that internal node is all your is coming under your cardinality of T, right?
Child nodes of that.
Yeah, what is that cardinality of T? Cardinality of T is like say for example, I choose a particular tree internal node. Okay.
No, you just choose a subtree of that fully grown tree. Here T denotes the subtree of that fully grown tree, T node. Now how many leaf node will be there? That is gonna be your cardinality of T. I don't know whether we call it cardinality of T or not, but it is denoted by mod of T. It is the number of leaf nodes in that subtree.
Okay, number of leaf node in that subtree. Okay.
Yes.
And even QT is for that particular subtree, right?
Yes, subtree.
But now in that subtree, like it is not necessary that, say for example, it is the total depth of the tree is 5. Okay.
Here we'll check for all possible subtrees. Remember, for a finite tree, what I mean by finite tree, the maximum depth of the tree is finite. So for a finite tree, there's gonna be finite number of subtrees, right? So we will check the value of CT for all such finite number of subtrees, and we will check for which subtree it is minimum.
Yeah, can we take a precise example and do that? If you can open up a white paper instead of telling like this, can you take a white paper and
So let's move to this tree, this particular tree. Yeah. So this is your fully grown tree, right? Now in this case, these are your leaf nodes. This 5 leaf nodes are there, right? So what I'm doing, I'm checking all the possible subtrees of this. So what will gonna be possible subtrees? So remove these 2 nodes, this particular 2 nodes. So this is gonna be one particular subtree, right?
See, that's what I'm telling you. If
subtree,
see, in this example, the depth of the tree is only 2, right?
Okay.
If you take a deeper tree, assume the depth is 5, okay, and at level 2 you are pruning.
No, to prune back from the last, we will check for all possible subtrees, not just a internal node. We just check for all such possible subtrees.
Can you like all the possible subtrees means like for a full grown tree you will find there will be 2 to the power n number of subtrees, right?
What is n?
Like whatever the depth is, roughly that much subtree, right?
Why to raise to power n?
Say for example here how many subtrees are there? Say for example this is there are 2 subtrees here, right?
No, why 2 subtrees? There you can make different subtrees. This is one of your subtrees. Remove this particular split. Then you will end up some different subtrees, right?
See, humidity is 1 node and wind is 1 node. Okay.
Yes.
So that means if I prune from there, so wind, whatever the tree below it is a subtree. Humidity, whatever the tree below it is a subtree, right?
No, we don't take this as a subtree. We always take backwards, right? So if we are removing, we first remove this one and then we'll check for this. It's not like we just remove outlook from the data set. Then there is no split and there's no sense of checking for pruning back. We check from the backwards.
Okay, so that means you are saying like you will check from the bottom and then go 1 level up and then you will try to prune, right?
Yeah.
Okay.
Okay. So any other questions?
Yeah, and another question is, this tree is the algorithm itself is very localized, right?
What does it mean?
That means it cannot check that say for example whatever the split it is going to do now, okay,
Yeah.
whether that will lead to a good split or not, it is not going to check.
That's why it is called greedy search. That's why this algorithm is called greedy search.
Yes, so correct. So that is the reason it is localized also, like the impact is localized.
Yes.
Okay, and another thing, like say for example, I believe there are some question like when you handling that continuous variable, right? Okay. So extending that further, say for example, what kind of pre-processing will be appropriate for this tree?
So feature scaling we need not to do.
So sorry to interrupt. Rajiv and Nitin, can I request you to hold off till the end, because
sure.
Yeah,
Okay,
because
perfect.
almost an hour is gone and we have 3 more weeks to cover. So
Yes,
just
sir.
a kind
Okay.
request, and after once the revision for all 4 weeks are done, we'll take up those questions also. Okay.
Yes,
Okay.
sir. We can take week 10 now.
Thank you.
Hello everyone. Okay, we am not able to share my screen. Give me a moment. Let me tell. So, anyway, give me a moment. I'm not able to share my screen.
Okay. Okay.
Okay, hello everyone. I hope you can see my screen. We'll now move on to the revision of week 10, which focuses on ensemble techniques. So what we have covered in this week are techniques like voting, bagging, and boosting. Bagging is similar to voting. We'll see what the difference is. So in particular, bagging and boosting are the two different kinds of ensemble techniques. And there are different variants under bagging and boosting. What we have covered in this week are random forest under bagging and gradient boosting and adder boost under boosting. There might be a couple of more techniques, but this is what we are focusing on, and this is what we will be discussing today. So in ensemble methods, what we do is we take multiple estimators. So far, we have taken one single estimator, and we've been trying to make it better by tuning the hyperparameters. That's what we did so far. Now, using ensemble methods, what we do is we take multiple estimators, and those estimators might not be as good. They might be simple estimators, generally called weak learners or weak estimators. And then we combine the outputs of these different estimators in some manner, which we will talk about. And that aggregated output is used to make the final predictions. So that's what is the broad idea of ensemble methods. And they are known to improve performance in most cases. Such techniques do provide a better performance, mostly in cases where the individual estimator has low bias and high variance. This particular problem is easily handled by ensemble techniques. So as I said, voting is similar to bagging. So roughly you can divide ensemble techniques into bagging and boosting. Okay, the difference between bagging and voting is that in bagging, there are homogeneous estimators. That is, all estimators are of similar type. In voting, you can have different kinds of estimators. Like you can have, KNN, logistic decision tree, different kinds of estimators you can bring in. That is your voting. In both the techniques, that is voting and bagging, what we do is we take the majority voting. I'm sorry, for classification, we take the majority voting, and for regression, we take the average. That's what we do in both voting as well as bagging.
Try to be loud, please.
Oh, is it? All right. I think I'm loud enough. Anyway. Okay. All right. So that was your voting or bagging. And in boosting, we start with weak learners and we take weak learners in sequence so that overall we get a strong learner. So that's the idea in boosting. Another thing is in bagging or voting, we use a parallel method in training. We parallelly train the different estimators and then we aggregate. So since we're aggregating, it's possible to do it parallelly. Whereas in boosting, the subsequent estimator works on the problems that the previous estimator had. So it is essentially sequential. Okay, now what's the majority vote? It's as the name says, we would have different classifiers. These are different estimators that we were talking about. And then they would provide some estimation. And then in case of classification, we would take the majority vote and that would be your final prediction. If it is regression, these will be regressors and whatever you get out of these estimators, you would take the average. That would be your regression. Now, let's see why this should work. Okay, let's take an example. Let's say we have 11 estimators. We're talking about classification. And let's say they all have error rate to be 0.3. So this is essentially the probability of wrong prediction. Okay, let's say each of these estimators has a probability, 30% probability of wrong prediction, 70% probability of correct prediction. Okay, now since we are going to aggregate, how do we aggregate the majority vote that we talked about? That is, the ensemble makes a wrong prediction if more than 50% of the classifiers make a wrong prediction. So we are using majority vote. Now, when would your ensemble make a wrong prediction? If more than 50% of the individual classifiers make a wrong prediction, right? Now, let's see what would be the probability of that happening. That would happen, what would be the majority in 11? The majority would be 6, right? So all 6 out of these 11 to be making a wrong prediction, what would be the probability of that? That would be this. 0.3 is the wrong prediction, 0.7 is the correct prediction, and that is given by 5 predictors. Wrong one is given by 6 predictors. So this is the probability of the ensemble giving us the wrong prediction, which is way too less, right? That is a broad idea of why sort of wisdom of crowds should work. Okay, why ensemble or majority voting should work. Okay, voting is of 2 types that we can use in case of classification: hard voting and soft voting. Hard voting is just what we spoke about just now, the majority vote. In case of soft voting, we go one level deeper, in the sense you would have seen the probabilities that each class is getting. Whenever we use any classifier, we get some probabilities. So if the probability for first class is 0.2 and the probability for second class is 0.8, the predictor returns the second class. But this underlying probability is what we make use of in case of soft voting. So what we do is we take into account this probability, these probabilities 0.2, 0.8 by first predictor, second predictor, and all the predictors, and then we take the average of all those, and whatever is the max that is predicted as the class, as the output class. So that's your soft voting. In case of regression, we just take the average. Okay, now we move on to bagging. As I told you, the difference between voting and bagging is, in voting there can be heterogeneous classifiers, while in bagging there will be homogeneous classifiers. trained on different data sets. In bagging, we train on different data sets. That's another thing to note. Now, why this name bagging? It's actually a short form for bootstrap aggregation. Now, what is bootstrap? We'll talk about. Aggregation we have spoken about already. All right, with a view to improve the accuracy that is there. Now, I'm sorry. Bagging is especially beneficial when dealing with predictors that tend to overfit data, right? That's the case in decision trees. We know that, we've talked about that. Decision trees will give you zero training error if you go on and on, right? But the test error will be high. That's your overfitting. That's because they memorize, and that's why we need multiple decision trees, right, instead of one. So these multiple decision trees, what will they say, will take the majority, and then there is less chance of overfitting. So that's one idea why bagging works. Now let's talk about bootstrapping. So bootstrapping generally is randomly choosing the samples from a given data set. Okay, let's say this is your original data set with 10 samples. So if you are asked to create a bootstrap out of this sample, what you will do is you will create, generally the size of the bootstrap is same as the size of your given bunch of samples. So there are 10 samples. We'll take out 10 samples for each bootstrap. How we would do that is we'll randomly choose one out of this. We'll randomly choose one sample and then we will put it back. So bootstrapping is essentially with replacement. Okay. So you let's say you randomly choose one, you get X8, you put it back, so that you could get X8 once again. So that's why okay, here you're getting X8 3 times. So that's what is the whole idea of bootstrapping. You get samples again, and you are not picking certain samples. That is what is happening. Similarly, second time if you choose, you might choose some other samples again, but the size is the same. So these are basically your bootstraps, and these are what are used in your bagging technique, where you will give different bootstraps, that is different data sets. So these are our different data sets, 3 data sets we have here. These will be given to 3 different decision trees. So now each decision tree has got a different copy of the data set, and that's how they will train, and that's how there'll be some difference in how they have learned, right? So that's the kind of data set that we use in bagging. Now yeah, this is the same thing that we just spoke about. N is the number of samples in the given data. We will have some Q bootstraps where each bootstrap will be of this size N. Okay, and we'll train different decision tree. Okay, we're talking bagging, so it's generalized technique. You can have any base classifier, not necessarily decision trees. So you will train a base classifier on each of these bootstraps. Okay, and these base classifiers will give you some prediction. So you get some Q predictions, right? And then you for any data point that you want to make the prediction, you will, in case of regression, you will take the average. That's your general bagging algorithm. Okay, now let's talk about a special case of bagging, which is random forest. The difference between bagging and random forest is that in random forest, we a subset of features. That's the crux. Every decision tree will be given a data set which will have a subset that will be decided. Let's say X features every decision tree will have. They will be randomly chosen. So that's what happens in random forest. So random forest is bagging with decision trees. So in random forest, use decision trees. That's why the name, tree forest of trees. So what few data sets as before. That's for each of these bootstraps that we have created, a full decision tree with one small modification, that is randomly sample u of m features without replacement. So that's the thing that we were talking about. So the only difference that the random forests bring in. Okay, the prediction is done the same way. Okay, just like we spoke about in bagging. So that's the same. Now, two hyperparameters.
Ma'am,
Everybody trying to speak? Yeah.
can you be little louder, because I hardly can make out actually.
Oh my God, is it okay? I think I'm speaking quite.
I hardly can make out.
All right, I'll try. Okay. Is it little better?
Far
Yeah,
better.
it is a better, yes.
All right. Okay. Okay. So you can think of two things that we need to tune in case of random forest. So how many base estimators we should use, right? That is Q, the number of classifiers. Second is how many features we should give to each of these base estimators, that is U here. So these are two hyperparameters that you might need to choose. Now, one thing that you can keep in mind is, even if you don't know how many, how much Q and U you should use, you can have Q as large as possible. You know why? Because we're taking the majority vote, or you're taking the average. So when you average things out, more the better, right? Majority voting, more the better. So you can have a very high Q value if you don't want to tune parameters. And there's a sort of rule of thumb for having how many features you should pose to each of the estimators. You can either take square root of total number of features, or you can take log of that. So that's these are two values that generally seem to work. Or you can do your, grid search or whatever. You can tune your parameters. Okay, now moving on to boosting. Different classifiers in the same training data. So we saw in bagging, there were different copies. These different copies we got out of bootstrapping. In boosting, we don't do that. Why called boosting? Because we are sort of, okay, firstly, it is sequential. That's what we talked about. Now, second, so we start with one estimator. Second estimator will try to work on the problems that the first estimator had, and so on and so forth. So we are sort of boosting in that way sequentially on the same training data. So we'll start with one training data. Of course, we will make some modification in terms of weights that we will talk about, but the data copy is same. That's what we want to emphasize here. Okay. We build a model on the training data set. Then the second model is built to rectify the errors, as in the first model, we spoke about it. This procedure is continued until and unless the errors are minimized, right? So we start with a weak model. Now, what is a weak model? Sometimes you might have seen weak learners. So what is a weak learner? Weak learner is one that is just a little better than the random one. So randomly, if you have to choose something, it will be 50-50, right? If there are two kinds of things. But if you have a weak model, it should be a little better than random choosing. So that's your weak learner. And these boosting techniques generally use weak learners. We'll see how they use them. Each model is fit on a modified version of the original data set. Okay, that's what I was speaking about. What kind of modification do we make in the original data set? That is in terms of weights. That's all. But the data is the same. Okay, we spoke about it. Weak learner performs a little better than random one. Now, boosting is an iterative process, right? Because it is sequential. And the training set is reweighted. Okay. How is it is reweighted, we'll see. And yeah, based on the mistakes of the previous one, right? Now, in boosting, there are various techniques. We are focusing on gradient boosting and ADA boost. Okay. Okay, let's see what gradient boosting is. So what we do is in gradient boosting, we'll start with one estimation, and that estimation is generally taking the average. Now we're talking about regression here. So we'll take the average. So you have your feature matrix X, you have your Y vector. You'll take the average of that those Y values. That will be your prediction. Let's call it the initial predictor. So that's your first predictor, which is weak learner of, obviously, as you can see, it's just averaging. It's your weak learner, and obviously it will make a lot of error, right? Now, moving on to the second step, what we do is we'll create, so visualize your X matrix, visualize your Y vector, visualize a residual vector. After your Y vector, let's have a residual vector. That residual vector will have the difference between the actual Y and the predicted Y by the first weak learner. Okay, so we got the residual vector, which is the difference between the actual Y and the predicted Y. And this predicted Y came from the average by the first predictor. Now we have this residual vector. Now what we'll do is the second estimator will come. That will be trained not on Y, but on this residual. Okay. I hope you are able to visualize the kind of the way I'm telling you. Okay, so we have now second predictor, and this is trained on the residual column. Okay. Now, okay. Now let's stop here. What we have so far is the first, we have the prediction made by the first predictor, that is the average, and we have the prediction made by the second estimator, which was trained on the residuals. Okay. Now in order to make the actual prediction, we'll combine these two. How would we combine these two? One way is just add them up. We have some prediction from the first estimator, we have some prediction from the second estimator, add them up. This is your final estimation. Okay. Now you can think that this can overfit. If you keep doing this, why? Because what you're doing is essentially whatever is left behind, you're training your model on that, you're adding that up. So whatever little was remaining, you're trying to learn that also. So this is precisely the kind of thing that decision tree does, right? So this has a tendency for overfitting. Therefore, what we do is we bring in an alpha, which we call learning rate. So what we'll do is we'll take a fraction of the estimation made by the second predictor. Okay, you can consider this to be first prediction. This is second prediction. Next would be, let's say, F1 on X train. Next would be F2 on X train, and so on. This alpha is the learning rate, and thus this will be same for all the estimators. First one is separate, but for all forthcoming estimators, this alpha will be same. So that's one thing to note. In gradient boost, this learning rate is same. This alpha is same for all estimators. You can take it like, say, how much say a particular estimator has in the final prediction. So let's say we take this alpha to be 0.1. So this estimator will have 0.1 say in your final prediction. Okay. You would have heard that there is a trade-off between the number of estimators and the learning rate, right? So let's say you have this alpha to be 1. Okay. Then you just need one estimator, one other than the base, this initial one. You just need one estimator. So you stop here. Okay. But if your alpha is small, you will have more such estimators in sequence, and then you will take little from all these, and it is known to improve the results. It is known to avoid overfitting and provide a good estimation overall on the test data. Okay, so that's the base. That's the main idea of gradient boosting. I hope that is clear. So this keeps we keep on repeating this. So after one estimator, you might have some more residual, right? So imagine you have one more residual column, let's say residual 2. Now your next estimator will be trained on residual 2. Okay, again you would have some errors, that let's call it residual 3. Your next estimator will be trained on residual 3, and so on. And all these predictors have some prediction. You multiply alpha with that and add them up. That's your final prediction. Okay, I hope that is clear. That's your gradient boosting. Now let's move on to AdaBoost. Okay, no, short form for adaptive boosting. Now, what's the main difference between gradient boost and ADA boost? So in gradient boost, we were working on residuals. We were training on residuals, right? In ADA boost, what we do is we assign a weight to each sample. Okay, and we'll keep on varying the weights of the misclassified samples. So let's start with one estimator. It will make some errors on some samples. We'll increase the weights of these samples, and then we will feed the same data to the next estimator. Now, the samples which have high weight will be considered more by the next estimator. So that estimator will be trained accordingly, and the error will be minimized. But then second estimator might also make some errors, so we'll increase the weights of those, and also we will decrease the weights of those which were correctly classified. That's also something to note. So the samples which are incorrectly classified, we increase the weights of those. The samples which are correctly classified, we'll reduce the weights of those. And that's the kind of data set that we'll send to the next estimator. So that's one thing to note. Second thing, unlike gradient boost where each estimator had the same say, in ADA boost, each estimator will have a different say. And what would that depend on? That will depend on how good they are. For example, if we talk about classification, if the classification error made by them is small, they are good enough. They are good, and we will provide them more say in the final prediction. Okay, let's see how we do that. Before that, yeah, so we use a number of B classifiers, and ADA boost uses decision trees with one depth, which are called decision stumps. Now, can you visualize a decision tree with one depth? There's only one splitting point, right? There's only one variable on which they are splitting, only one feature they're deciding on. Whereas in an actual decision tree, we consider all the features. These decision trees are indeed very weak because they are only considering one particular feature. But the next feature might be considered by the next estimator. So that's how it works. Yeah, okay. So it builds an initial model while giving equal weights to all the data points. So let's say we have 20 data points, we'll assign 1 by 20 to each of the data points. They should sum up to 1. So that's the kind of weight that we assign. And then we will fit on the first estimator. Okay. It then assigns higher weights. Okay, let's say the first estimator is done and we got some samples which are misclassified. Now, what we will do is for those particular samples which were misclassified, we will increase their weights and we will decrease the weights for the samples which were incorrectly classified. How we would do that, we will see in a while, how we exactly will change the weights. Now, all the points which have higher weights are given more importance in the next model, right? That's what we spoke about. So in that way, each model compensates the weaknesses of its predecessor, right? It will keep training that way. The final model uses the weighted average of individual models. Now, how this weighted average is seen? This weighted average actually considers the say that we were talking about. That's actually the performance. That's what we've used here. The performance of each classifier that is considered when we are giving the final prediction. Okay, it works by putting more weight on difficult to classify instances, right? And less on those already handled well. All right. So as an example, what's happening here, this is your data, and then we apply model 1 on this, and then we see that these 3 samples are misclassified. So what we will do is we'll increase the weights of these. You know what, we should actually reduce the weights of the others. That's something that should have been done. So you should decrease the size of the rest of the samples which were correctly classified. That happens. Now that is what is given to the next model, which is model 2. Okay, and then model 2 will also misclassify something, and then we will increase the weights of those and will reduce the weights of the others and will feed to model 3 and so on. And for final prediction, we will consider all the 3 models as per their performance. That will be your final output. This is what we just now discussed. Now, what's this performance of each individual estimator? The thing that we were calling say of a model, that's the performance of the model. This is the formula that is used. Now, what is this total error? Total error is actually the sum of the weights of the misclassified samples. You remember we initially gave 1/20 weight to each of the samples. Let's say 3 samples were incorrectly classified. So total error for that model would be 3/20. Okay. Now 1 minus 3/20 divided by 3/20 and log of that, that is the performance of that model. Now, you can see here, if the error is high, this will be small, this will be small. The performance of that model will be small. On the other hand, if this error is small, this will be high, this whole thing will be high, this performance will be high. Okay. All right. So yeah, now where do we use this performance? Okay. This performance is used in 2 places. One, for updating the weights of the samples for the next model. Second, in the end, when we are making the final prediction. Okay. In these 2 places, this performance alpha will be used. Now, how it is used, let's see. Okay, we spoke about the thing that misclassified samples, we increase the weight for them. Correctly classified samples, we reduce the weight for them. We also take into consideration the performance of the model that actually gave this prediction while updating the weights. So what I want to say is, let's say this weight old is the old weight, let's say 1/20 that we started with. Okay. Now that model made some performance alpha. Okay. Since the model performed well, but could not classify this well, so we should increase the weight of this sample. Correct? Makes sense? All right. That model performed well. On 17, it performed well, but only on 3, it could not perform well. So we should increase the weight of these samples, because by a good model, these were not predicted. So they are tough cases. So let's increase their weight. That is why we are multiplying with e to the alpha. That is, it penalizes more if by a good performing estimator, the error is coming. Okay. On the other hand, for correctly classified samples, as I said, we will reduce the weight. Okay. So e to the minus alpha will reduce the weight. This is the old weight, 1/20. Now, when you multiply with this, the weight will be reduced. So this is how the weights are updated. Okay, yeah, that's all. So that's how we go on in AdaBoost. So any doubts we can take now.
So ma'am, here weight means like weight of the the classifier, whatever it learns, those weights, or the points you are giving, associating some weight to the points those data points.
Data points.
Okay.
Samples. Yeah.
Samples.
So as I said, initially, let's say 20 samples are there, and we give equal weight 1/20 to each. But after first model is done, the weights will be changed as per these formulae.
Mm-hmm. Okay.
Ma'am, Shreya here.
Yeah.
Any chance you got an update on yesterday's question where we set the learning rate to a constant value?
Okay. Okay. Are you talking about AdaBoost itself in Sklearn?
Yes.
Okay. Yeah, I checked, Shreya. So if you see, okay, if you see in Sklearn, gradient boost, the alpha value is 0.1 by default. Okay.
Yeah.
And in AdaBoost, the default value of learning rate is 1. Okay.
Yeah.
Now, the learning rate that we spoke about in gradient boost, it is that learning rate in Sklearn.
Okay.
This alpha. This
okay.
alpha. Okay, 0.1.
Okay.
Whereas in AdaBoost, we compute it during the model. Okay, this okay. Actually, the variable should have been different to avoid confusion. This alpha is different. Okay, that alpha in gradient boost is learning rate, same as the Sklearn learning rate. This alpha in AdaBoost, this is not a hyperparameter. Okay, This is what is computed as a part of the model. This is not something that we supply.
So what
Learning rate is in sklearn is 1. So it's actually it actually won't make any difference. So what will happen if you change the value of that learning rate in AdaBoost sklearn?
Yeah.
I said that finally, how would you predict? So let's say you have done your prediction. You have done your training, and now you have to make the final prediction. So let's say we're talking about classification, and we have the prediction made by each model. We also have the performance of each model. So we will see, let's say there are 2 classes, yes and no. We will see how many models are making a prediction of yes, how many models are making a prediction of no. And then we will add them up. We will add up the performance of these estimators. Okay. Whichever weight is, let's not call it weight, sorry. Whichever sum of performance is more, that will be the final prediction. Okay. Now, when you introduce this learning rate, sklearn learning rate that we're talking about, it will multiply the performance by that very parameter, and that will be constant for all. So, in my opinion, that should not make any difference. But we can check this out. So, did you get my point?
No, I'm not very clear on how the prediction part works. I think so okay, let me just ask that. So other than gradient boosting for regression, we don't need to know how and of course bagging, we don't need to know how predictions are made for the others, right? Because gradient boosting, classification, AdaBoost predictions are not covered here.
I'm sorry, I didn't get your question.
So if I were to make a prediction using AdaBoost, I don't know how to do it.
What is your doubt?
Like I'm just saying we don't need to know those things, right? Like if there'll be no questions like.
Okay, you're asking for from exam perspective.
Yeah. Sorry, I should mention that.
Don't worry about exam. Focus on understanding the concept. Anyway, so yeah, you might not be given to solve as such. You should know the algorithm, but yeah, you would not be asked to, at least for final exam, you would not be asked to solve and do the prediction. Yeah. But let's talk about whether you understood the algorithm or not.
No, I actually, without I didn't quite understand how the prediction happens in AdaBoost.
Let me tell you. So in AdaBoost, continuing the AdaBoost itself, so we have, let's say we have 10 models, and we have a prediction. We're talking about classification. We have a prediction made by each of these 10 models. Okay.
Right.
And there are 2 classes, let's say yes and no. Let's say 6 of these models are making a prediction of yes, and let's say 4 of these models are making a prediction of no. Okay.
Yeah.
Now we will see the performance alpha, right? Yeah, alpha of each of these 6 and 4 models. We'll sum them up. On the left hand side, we have the models. We have the performance of the models who predicted yes. On the right hand side, we have the performance of the model. Some of the performance of the models who predicted no.
Okay.
We'll sum them up. Let's say the 4 models which predicted no have a high sum alpha. We will make a final prediction no, despite the fact that only 4 were saying. That's why this is not majority voting.
Okay. Understood. Okay, so it's.
So ma'am, this alpha is going to calculate like it has to be calculated for all the models, like for your 10 models, right?
You are expected to do that, because how else would you update the weights? In every iteration, you have to update the weights, which is making use of this alpha, right? So you have to compute that alpha. So that's why I told you alpha is being used at 2 places. One is while updating the weight, second in the end while making the prediction. Okay.
No. So, this alpha is here like 1 minus total error by total error with ln. Okay. Now, what is this total error actually? This is by
go on.
Yeah, is this total error by the individual classifier or?
Yes. So here we're talking about one classifier. Total error will be the sum of the weights of misclassified samples.
Correct. So now if you have 10 classifiers, okay. If you have 10 classifiers, there will be 10 alphas.
Yes.
And then you are saying sum all these alphas.
Sum if we are talking about classification, you will sum alphas for all those who are making one class prediction. You will sum alpha for those classifiers who are making another class prediction, and we'll see which is higher. Whichever is higher will be the final prediction. Is that clear?
Yeah, but intuitively, this alpha is like how much weightage you are going to increase for those data points which are misclassified.
No. Sorry, come again. Alpha is?
Alpha is the value like through which you are increasing the weights, right? Like weights
Yeah,
of those
alpha is the
misclassified data
value.
points.
Yeah, alpha is the value which we are using to update the weights of the misclassified samples, right? So so alpha is simply the performance of a model. If the performance of the model was high, that is, the model was actually good because it predicted most of the samples well. Only, let's say, one or two it could not predict well. So you will take that into account, right? You will see what was the performance. Okay. Page rank, I'm good if good people link to me. Okay. If one good person has a link to me, I'm better than if 10 simple people, link to me. I mean, I hope that Google page rank is clear to you. That just came to my mind. So if the performance of the model is good, which means we will hear this model more, right? If the performance of that model was low, we won't hear it more, simply put, while updating the weights. Okay.
But say, for example, for AdaBoost, like you are giving that alpha times the output from the different regressor. Okay. There you are giving a
wait, gradient boost, right?
Yeah, gradient boost, like what you are doing, like you are giving a proportion that how important that that regressor is.
You're talking about gradient boost or AdaBoost?
Gradient boosting,
Okay.
like look at that. Yeah, this one alpha times f0.
Yeah, correct.
Okay, so that means f0 is the classifier 2. Say for example, classifier 2.
Yeah.
Okay, so now you are telling that okay, how much 2 is important for me.
No,
this is clear.
No. This is not importance here. See, alpha in AdaBoost is the importance. Okay, but that's what I was telling. Alpha in gradient boost is not the importance. It's just to handle overfitting. So what we do is whatever the subsequent models tell us, we'll take a fraction of that only. This alpha is not the importance. This is how much we want to take from each model. This is not at all the performance of these models.
Okay,
this is a hyperparameter, by the way. This is a hyperparameter. Learning rate.
This is a hyperparameter, right? Yes, because it is a linear combination. That's why you are saying it is a hyperparameter.
No,
because multiple f0s are coming.
Hyperparameter. I'm saying this is hyperparameter because before starting the model, the ensemble model, we need to supply a value of alpha. Okay, that's the fraction of the value that will be taken from each of the models. It has nothing to do with the performance of these models.
Yes, it is nothing to do with the performance of f0.
Yes.
Okay,
and it will be same for f0, f1, f2. It will be same.
Correct.
Yeah.
Now in case of a f1, like I'm just trying to understand how that alpha, like you are telling, finally you are now you are doing that voting as well, right? That six people are telling.
This is regression, right?
Yeah, this is regression, like gradient boosting. Now in case of a AdaBoost, what you told, so that 6 classifiers are telling me +1 and 4 classifiers are telling me -1. Okay, so that means like I will add up the 6 alphas and I will add up these 4 alphas and I will check which alpha is more. I will specify that, right?
Yes. Yes.
So intuitively, like this alpha is the error that is made by individual
No.
classifier.
Alpha is not the error. Let's not confuse in the terms, names of these terms. Error is this. That is
Yes, alpha is not the error, but some measurement of
alpha
like
is performance on the other hand. It's the opposite of error. It's a performance. Yeah.
Okay.
Okay.
Ma'am, one last quick question. One of the questions said that compared to the base classifier, a bagging will reduce the error while boosting may increase the error. Is that
Is it?
the
Where
right
is
statement?
this question?
It is there in one of the graded practice assignments of week 10, but that's not correct, right?
No, you're saying that bagging will reduce error while
Boosting may increase the error.
increase the error.
But it should be false, right?
Statement doesn't seem correct to me actually, or incomplete. Was it bias variance or only error?
It just says error.
Okay. Can you please start a post on this?
Sure, ma'am. But in any case, then if I replace the word error with variance, then does it become true?
Yeah, that's what I'm trying to think. So,
Okay.
bagging reduces the variance.
Correct.
And increases the bias. Yeah. So if you replace error by bias, it might be probably true.
No, it says bagging reduces the error while boosting may increase the error.
It's in graded, is it?
Yeah, I think
this doesn't look correct to me. I'll have to take a look.
So boosting generally works on the residuals, right?
Boosting, gradient boosting works on residuals.
Okay, if I like, since the question is framed like that, so if I take example of gradient boosting, it cannot do bad, right? The reason being, always you are taking the residuals and you are asking, okay, but do something better.
Sorry, I didn't get your question.
See, in case of a gradient boosting, you are taking the residuals and you are trying to improve upon that. So gradient boosting cannot deteriorate other than y trend 0.
Other than y trend 0. Yeah, it will improve. It will keep on improving.
It will always improve. It cannot deteriorate less than y trend p0.
Think about a case where your alpha is high, your number of estimators are also high. Okay. So it will bring in extra things in the end, which might not be correct. So that's why they say there's a trade-off between alpha, that is the learning rate, and the number of estimators. So let's say your alpha is 1, and let's say your estimator is also 1. I mean, other than this initial one, you have just this. So it will completely fit, right? It is possible. It might not also, but it might fit. It is possible. And whatever residual is there, that will be probably fit by the next one. So it's actually overfitting. Can you see that? I mean, if you don't introduce alpha, it will overfit. Can you think of that?
No, it cannot overfit as well. It cannot overfit.
It will overfit.
Overfit, Rajiv, no, because you are adding and adding.
Yeah, correct. You're adding and adding the residuals. Whatever error, whatever gap was there by first estimator, you're bringing that in by the second estimator, right?
See, overfit is always done by a single estimator, right?
No, why?
Single estimator can do the overfit, but here your estimators are like
overall estimator will do the overfit, right? Overfit, I mean, we're talking about a model. This is a model here, and this model will overfit.
No, but okay, like how it will overfit actually?
Okay, let's say your y was 20 and your first model, which was averaging, gave you 15. So the residual is 5, right? Now on this 5, I mean, all the residuals, the residuals of all the samples you will give to the second model, I mean, this model. And what will be the y for these models? That will be 5 and dash 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 and so on, right? Now this will try to learn some of that 5. Let's say this predicts, let's say 4. Okay. This model predicts 4. Now here we had 15. Here we got 4. Okay. The difference is 1, right? Now that one residual will be given to the next estimator. And let's say it also, learns that. So this 15 plus 4 plus 1 completely is learned by this model, which means it has overfit, correct?
Whereas but the training error 0 doesn't necessarily mean it is overfit, right?
That actually means, because the data is not deterministic, right? The real world data has noise, and that noise is also captured by your model, and that's why you're getting 0 as the training error, right?
But is it safe to conclude from that? Because I have seen some literature like where they are saying,
go on, please.
Yeah, where they are claiming that this gradient boosting and this boosting methodology, this will not lead to overfitting.
Yeah, that's why.
And there are some mathematical explanation as well. Like I don't understand them. That is okay, but there are some mathematical explanation as well. So that's what I am just reinforcing this thing.
Yeah, okay. So we didn't use alpha, which is an integral part of gradient boosting. We were just taking an example scenario where we are not making use of alpha. We were discussing that in that case, it will overfit. But alpha has to be used. We have to. So if you see Escalon default value of alpha, which is learning rate, that is 0.1. Okay, so that is why it takes something from this. It will take something from the next one. It will take something from the yet next one. It will not take the entire thing, and that's how it will handle the overfitting. Okay.
Madam, why is it called gradient boost? Why? Where are we calculating the gradient?
So not exactly gradient. We are not exactly calculating gradient here, but the residuals actually give the direction where to move. So in gradient descent, if you see, the gradients are giving the direction of where we should move, right? For in the next iteration. Right. Here, it's actually not the gradient computation, but the residuals are giving the way towards the next move. That's why it is called gradient boosting.
So, ma'am, just to confirm, bagging reduces variance but increases bias. Boosting reduces both, but they may also increase the variance in certain cases. Are those statements right?
Bagging was correct. Boosting, I'll have to check.
If it overfits, then in those cases, like they may increase the variance, right? I mean, that's
if it overfits, it will. But as I said, alpha is used in practical scenarios. We have to use alpha, so it will not overfit, right? That's why, as Rajiv said, gradient boosting techniques generally don't overfit because there are mechanisms there that handle this overfitting part. So we can't say that it overfits and hence variance is high. We can't say that. No. I'll have to check for the boosting bias and variance, but bagging was correct.
Okay, ma'am. Thanks.
Okay. If there are no more questions, we may move on to week 11. Sorry.
Thank you, Anika. Give me a minute. I'm just starting my desktop writing app. Okay, I hope it's visible.
Yeah, it's visible.
Okay. So let's start with week 11 content. So week 11 is the only week in which we are discussing unsupervised learning method, and in that, which is clustering. Okay, okay. So the question or the problem statement of clustering is that we want to group the data samples in certain groups so that within a group, the data samples are very similar to each other, and across the group, they are dissimilar. So this is in contrast to what we have already been seeing in supervised learning problems, where we had this X and this Y, but for clustering, we do not have these labels. Okay, all we have is the X, that is the samples. And now we want to figure out if there are certain groups or clusters that exist within the data. Okay. So the few things that we need to consider is, first is number of clusters. Second thing is, when we are saying that the points or the same data points of the samples within a cluster or within a group, they are supposed to be similar, and across the group, they are supposed to be dissimilar. So this measure of similarity or dissimilarity. Which is also actually distance metric. Okay, so now whenever we receive a data set which is not labeled, we do not know what is the number of good number of clusters is, and therefore the algorithm, which is k-means algorithm, that we are covering in this week, this k is a hyperparameter for this algorithm. That means we have to choose actually we have to experiment with different values of k, and based on a certain metric which we will be discussing, we are going to choose best value of k. So first let's take some toy data set. There are some data points. I'm deliberately making it so that they are, not overlapping and simple. Okay, now this is a data set. Though I have marked them with different colors, they actually belong to, they are not labeled, they belong to same data set. And just to mark or highlight the fact that they are linearly, I shouldn't say linearly separable, but because it is not a classification problem, but quite distant from each other. Okay, so these are the groups. So from clustering, what we want is, we want once we apply this k-means clustering algorithm, we want k is equal to be 3 by visually inspecting it. Okay. So what we do is, first of all, we need to what we do first, we choose some value of k. For example, if we choose k is equal to 2, initially we do not know what is the best value of k is, so we start with 2, and we choose 2 random centroids. So what we assume is, the clusters that we are looking for, they have some centroids, that is some centers, and all the points from that center are very, very close from each other, and the data points which belong to some different cluster must be far away. So what do? We choose some random points as centroids. So what our expectation is that the points from the points which are very close to a particular centroid should belong to that cluster. So if I the distance metric that we use is Euclidean. So what we do is, basically we are drawing two circles around these centroids. So it might look something like this. Okay. Something like this and something like this. Sorry, so let me draw just a part of it. Yeah, something like this. Okay, so this point actually belongs to this cluster. Now what happens is now we have assigned depending upon the proximity of a point to its to any cluster, which cluster centroids, which cluster it belongs to. Then what we do is we recompute our clusters. Okay, so we take average of these points. So basically in the next iteration, what we are going to do is we are going to cover these points for computing the cluster of for computing the centroid of this cluster, and similarly the second cluster will have a centroid computed from these points, and we repeat this process until number of iterations that we want to conduct has been reached. Or there are no there is no change in the assignment of data points to clusters. Okay.
Excuse me, sir. Sir, the iterations is to find the location of the centroids, is it?
Right. So every time we so one iteration consists of this thing: compute or assign points to centroids / clusters. And second step of this iteration would be recompute the centroids by taking means of the points belonging to that cluster. So this is your one iteration.
Got it, sir. So the number of iterations is also hyperparameter.
Number of iterations is also hyperparameter, right?
Why does that have to be? If we don't fix it, will it continue to keep happening?
Pardon me?
So I'm asking you that it will not, optimize on its own, is it? So if we did not limit the number of iterations, the algorithm will keep going.
So if you do not limit number of iterations, well, you can keep doing this computation for a very long time. But if there is no improvement, you don't have to continue running your algorithm. That's why this stopping criteria. And second thing, you are on a budget. You cannot wait for a very long time for for your algorithm to keep running. So you want to cap it off after some number of iterations.
Right. Thank you, sir.
Okay. So now we know how the algorithm works. So maybe after 2 or 3 iterations, or after converging, since we are forcing that this data set should be divided into 2 clusters, we might not get a very good clustering per se out of this algorithm. So what we have to do is we have to repeat the entire k-means algorithm with different values of k and see which value of k is going to give us very good results. In order to do that, we have to find out how do we measure which set of clustering is good and which is not. And for that, we have a definition for loss function. So assume that mu I is a centroid. There's an indicator function which indicates whether xj belongs to ith cluster or 0 otherwise. So I varies from 1 to n. N is the number of data. Sorry, I'm making a mistake. J varies from 1 to n, which is the number of samples, and I varies from 1 to k, which is number of clusters. So this is the formula we use to compute loss. So what it does is, if you look at this term, so it is computing the distance of every point belonging to ith cluster from its centroid, which is mu I. And if you do this, what it does is basically it calculates the for every cluster the same thing it does for what it did for ith cluster.
Okay. So this loss function is a convex function, right?
Sorry?
Is it a convex function?
Sorry, I cannot hear you clearly.
Is it a convex function?
Is it a convex function? Well, I can't say. Its first thing is that it is not continuous. Okay. And negative values of k is not possible. I have to look more into it before saying it is convex or not convex.
Okay, because we are taking that, we are telling like this has a problem like getting stuck into the local minima, right? And that is the reason we run this iteration multiple times.
Well, interestingly, yeah, Nitin, you want to say something? Oh, I thought, okay. So, no, so this loss function, even though it is written like this, we are not going to differentiate or, find a gradient of. So for k-means algorithm, we are going to find the best value of k in a slightly different manner as we did for other algorithms.
Sir, so won't this be plain values? Because I think this looks like a measure of dispersion in each of the clusters. So
Correct.
won't these be just numbers for each of the class?
Sorry, I didn't get that part.
The loss will be just a number, right?
Yes, it will be a number.
Okay.
Okay. So
Loss is always a number.
Yeah. So, okay. So just by looking at that formula, can you tell me for what value of k, this is always going to be 0?
Which is going to be 0? The loss?
This loss, yes.
1.
When the number of samples is equal to k.
Is the number exactly? That is absolutely right. That means every point belongs to its own cluster, and since every cluster has only one point, so the centroid will also be exactly that point. And if you take this quantity for every cluster in that case, you are going to get 0, right? But that defeats the purpose of clustering. We don't want to do that. If we do that, then we already knew that right? We don't have to do all of this work. So to determine what is the best value of k, we look at a slightly different manner of optimization. What we do is we plot this loss function with different values of k. Of course, for one it turns out to be something else, but it doesn't help us. So we start from 2. So for 2, let's say it comes out to be something over here. It's increasing over here and it's increasing over here. Then we try the same algorithm for k is equal to 3. And what do you think as we increase the number of k, should the loss be decreasing or increasing?
Decreasing.
Hopefully decreasing.
Yeah, it's more likely to decrease because as we are increasing the number of clusters, or the number of centroids will increase. So the data points will have more number of options to be closer to, and that's why it should decrease. So the next point, let's say, comes out to be this one. So you can see that there's huge drop for k is equal to 4. Okay, let's see if we see a drop like this, very small amount of drop, and 5, 6, and 7. And even if you run this algorithm with different real world data set, this is the kind of curve you will see. Okay. Now
it will go to 0 because you mentioned that before, right?
Exactly. If at this becomes
samples, yeah, it'll be 0.
Yeah, then it will be actually 0. It will touch over here. Right. So now how do we choose the best value of k? So we use this elbow method. So in the diagram, in this kind of diagram, we look at where the elbow point is formed, and it is coming out to be this one. Like if you compare this with a human's hand, and this is the elbow point. Imagine that. So this point gives you the best value of k. The reason for that, or the intuition for that, is because up to this point we are getting significant drop in our loss, and after that it is not doing much improvement. Therefore, this is the best value of k.
Yeah. So computationally, it is basically the change in slope is.
Change in slope.
Actually, we asked this question earlier also. I don't think we got a clear answer. How do we do it computationally?
See, right. We can do it computationally, but I wouldn't call it a slope because it's not a continuous function. What the slope would be at this point? That would bring us to a different, branch of mathematics. But let's not do that. What we can do is if you want to do it computationally, right? So let's say you have this loss array. For shorter notation, let me just call it L. You have this list of losses. What you have to do is you have to differentiate, or not differentiate, sorry, take a difference of Li minus Li minus 1. So what you do is just you subtract the loss value from the previous iteration.
Over Li minus 1, right?
Yeah, and for this quantity, you keep recording or comparing with another quantity. So whenever you get this to be maximum, or after that, or not maximum, I would say that there is a significant drop in decreasing of this loss value, then you can call it, okay, this is I is the perfect value for k.
Sir, why not call it maximum?
Maximum of what?
So you said you won't look for the maximum value, but maximum drop in loss should be the criteria.
Yeah. Let's say there could have been okay. So sorry, this chart is maybe if I had started this chart somewhere else. Give me one moment. So what I want to do is I want to take it somewhere else where I have the Yes, something like this. Okay, so imagine that this could have been here, and the drop from value 1 to value k is equal to 2, the drop is even bigger, right?
Yes, sir, got it.
Right. So therefore, we cannot be certain that even though drop is very, very large, does this largeness of the loss keeps continuing with increasing k. So for as we go from k is equal to, sorry, did I say k is equal to 4 is the best value? If I said that is wrong, k is equal to 3 is the best value for this data set. So the value of loss drops from k is equal to 1 to k is equal to 2, but it again drops significantly from k is equal to 2 to k is equal to 3. And from 3 to 4, it is not dropping as much. And that's why we say that this is the best value for k. Okay, before we move forward, any questions? All right.
I have a question, but I'll ask it after you finish.
Okay, sure.
So I have a question now.
So what are the advantages and disadvantages of k-means? Is the advantages are it's very easy to implement algorithm, and it uses Euclidean distance, so somewhat sometimes it can be an advantage and disadvantage as well. The disadvantages of this algorithm is it is computationally very intensive. Second thing is we do not know what is the best value of k is, so we have to repeat the same process many times and figure out what is the best value of k by looking at this chart. For large data sets, it could be very difficult. So it takes a lot of time. Another problem with this algorithm is the random initialization of these centroids can affect your clustering, okay, in some cases. So what happens is for the same values of k, you will have to repeat the entire process by choosing different centroids initially. Another problem with the k-means algorithm is that it is not very good with non-spherical clusters. So if I remember correctly, so there was this chart in the slides that's covered. I shouldn't say plus or minus.
Yeah, that moon-shaped stuff, it cannot.
Exactly like that. And the other one was something like this. I've color coded so that you can imagine that blue is one cluster and red is another cluster. But if we go with k-means clustering, even if we give k is equal to 2, it is always try to squeeze in the spherical clusters, and therefore it will make mistakes. Yes, I think that's all from my side.
So for lower
One
value,
question. Sorry, on the
Yes.
silhouette, what is the formula to be used?
Good question. So the silhouette formula that has been mentioned in these slides is actually incorrect. Yeah, the corrected version is a bit different.
Yeah, so should we use suppose we get a question because the graded question assumed AB, right? It gave me a wrong answer for anything else. Should we say A minus B divided by max AB, or should we follow the slide?
No, you should follow the correct one, not the slide. We'll correct it definitely. Yeah.
Yeah, and can you like a little bit elaborate on that silhouette distance, like because it can take value between -1 to +1, right?
Okay.
Now, say for example, one part of the silhouette distance is like how cohesive the cluster is.
Okay.
And another part of the silhouette distance says like how what is the amount of separation between the clusters.
Right.
Okay, so now from that, like I can understand if silhouette distance is 0, then both the clusters are kind of overlapping with each other.
Okay.
But what is the intuition being -1 and +1?
Okay. Okay, Rajiv, give me a few minutes. I'll come
Okay.
back to come back to you on that in the same session. In this session.
Okay, bro.
There is this question in graded assignment. I'm sorry, Trivikram, I'm sorry.
Sir, for lower values of k, it's going to overfit, right, in this algorithm?
Well, I wouldn't call it overfitting or underfitting. The reason for that it is not supervised learning problem.
Okay, but the concept of overfitting and underfitting will still be applicable here, right, in a way?
Well, it's no, I wouldn't say that.
Okay, it's only for supervised then. Is that so?
It's only for supervised learning, right? How I mean, how would you say that this is? We don't have test data. Test data is the benchmark using which we say that whether our model is overfitting or underfitting. We don't have anything like that in here.
But say for example, given a new data, you will like to predict what will be the level for that, right? Like which cluster it will belongs to.
Yeah, that we can do, but we cannot guarantee whether it is overfitting or underfitting. How can we do that?
Because we don't have a picture of the reality. We don't know the reality. For the supervised learning, we know the reality against which we can test our model, but there is no reality in the.
We don't have ground truths. Yes.
No, but like your underfitting, overfitting doesn't depend upon the reality, right? It depends upon the loss, training loss and test loss.
Okay, so right.
And you have a defined loss function, right?
Loss function, okay. And
so
to
now,
compute loss function, you will need labels, right?
No, not necessarily. Like now you calculated the loss, right? You have a loss function like how much, what is the distance from centroid, and that way you and then you take the norms and double sum over the entire stuff, right?
Okay.
Now this is the set of data that someone has given it to you, okay? And now say for example you have been given another set of data. Okay, now in that set of data, you might see that with this set of clusters, okay, this model, when you apply on that data, it is throwing like a lot of error. So that means it is overfitting, right?
No. When you so you are saying that you have one data set in which you have figured out the number of clusters and the clustering also. You use that same centroids and clustering and apply it on different data set. It will not work, right? Why should it work?
So just to add, how will you define error in the second case? It will always belong to one cluster. What will you compare against to call it as a huge error or?
Okay. Say for example, okay, perfect. Say for example, you have a X. Okay, you divided that into X train Y, X train X test.
No. That was not a question. I was just saying that it can't be overfitting because of that reason. There is no metric to say that there's an error.
Right.
No, but like if you think in this way, say for example, you have 10 data, okay, 10 samples. You have taken 8 samples to identify the clusters and then project these 2.
But Raju, how you know that 8 cluster will go to which cluster center? You don't know. That is the problem. If you are initializing the cluster, you are just initializing the value. Okay. That's why initialization of a centroid is very important. Otherwise, it will never go to converge.
No, so that means you are saying like, see here, like whenever you are getting a data, that means you got it some distribution function like from where the data is generated, right? Now you have come up with some cluster and later on like with that same distribution data is getting generated. And then
no, if you have distribution,
some ground truth, and then only you are telling that okay, this is the correct data or that is the wrong data, right? That's what.
See, Rajiv, Srinivasan here, we may not even assume a distribution function, right? It could be anything because we don't know such things. Without labels, it's difficult to get those things.
So see, I'm telling you some real life problem. Okay, say for example, you have a manufacturing process and that process is generating some data for which the that data is getting generated from some distribution, right?
Right.
From that process. Now, you took certain data, say for example 5 years data you have taken, and then you clustered it, and then you understood, okay, like the data that is getting generated probably will be put into these 5 buckets, okay, 5 clusters. Now, next like a 1 month data, like which is going to get generated, when you project on it with that cluster, you see more errors.
Yeah, that means when you are telling about the 5 cluster it should go, that means you have the ground truth now. But when you are training it, you don't know the ground truth, correct? So once you got the ground truth, then only you can tell, okay, to go to which bucket. That means you know what is your ground truth. Is it is a 1, 2, 3, 4, 5. But in reality, it is not happening. You don't know the ground truth at all. That's why everybody is telling that there is nothing called overfitting or underfitting in the supervisor.
Can I add a small point here, Mukesh? So I think there was something about overfitting and underfitting. Although since it's not supervised, there should not be overfitting or underfitting concept here. But if you want to look at it that way, what I can say is, if you increase the value of k, so here the kind of error that we're looking at is the distance. The objective is to reduce the distance from the centroids. So when you increase k, so let's say your number of samples are 100, and let's say as an extreme case, you take k to be 100. In that case, the error will be 0, right? Yes, so that is a sort of overfitting here as compared to, let's say the the actual number of clusters are 10, and you're taking k to be 3. Now, sorry. In that case, you can say that you're sort of underfitting. I mean, if you want to look at it that way, although that only applies to supervising.
That case is correct.
Yeah.
Sorry, ma'am, can you repeat once again? When are we overfitting? When is that concept coming into the picture?
Yeah. So I'm saying, let's say you have 100 samples, on which you are applying clustering, and k is something that you don't know. Now, let's say as an extreme case, you take k to be 100. In that case, the distance from centroids will be 0. I mean, the error that we are looking at, that's the objective here, which will be 0. That will be a sort of overfitting in this case as compared to, let's say k is equal to 3, where you are actually not exploring the clusters available. More than required number of clusters are going in one cluster. I mean, more than, wherever there should be, the actual numbers are, let's say 10, and you are putting everything in 3 clusters. So that is a sort of underfitting, if you want to.
Yes, got it.
Ma'am, here just that k being large can be a desirable trait also, right? Here, unlike a supervised learning, where overfitting
not always. It actually depends on the data, right? We can't say that k being large might be a good idea. Of course, when you increase k, your error might reduce because the number of centroids will increase, and hence the errors will reduce. But then that's why these measures are there. These elbow plot is there, and other measures are there. And I think Srinivasan also had a question how to do it computationally. So there are actually different ways to computationally look at it. I mean, finding the value of k. So one way is your aim should be to have smaller intercluster distance and higher smaller intra-cluster distance and higher intercluster distance. So this is one measure that is sometimes used in practice to computationally find the value of k. There are different measures, you can look at them. I mean, if you don't want to go plot way, you can do it computational way also.
So ma'am, that is basically included in the silhouette distance, right? Intercluster and intercluster.
Okay, yeah, silhouette, yeah, that's what you sort of do. So using intercluster and intracluster, there are different ways. Silhouette could be one of them, but there are different, I would say, I've seen more than 10 papers on it which do it. Mm-hmm. So there are ways and you can try them out if you want to do it computationally.
Ma'am, silhouette distance is computed for all the clusters, is it?
That I'll have to check. I'm not sure. I'll have to check that silhouette distance formula. I think that's once computed, right, for all the given.
It is for each point with its respective cluster, right? So it has to be that.
Each point.
Yeah. Okay.
Ma'am, can you please update the right formula of Silhouette score?
Yeah, that has to be updated. Okay, in the slides, we might need to annotate, but
So, do we take as B minus A by max of BA?
Yeah, that only.
Yes.
It's a B minus A or A minus B?
B minus A, because B is the inter-cluster.
Okay, B minus A divided by max of A comma B, right?
Yes.
Okay.
And what is A again? Sorry.
A is the cohesiveness. That means in a cluster, what is the maximum distance between the furthest 2 points?
Okay.
In one cluster.
Okay. Got it. Inter-cluster distance minus the maximum distance in a particular cluster by the max of both inter-cluster and...
Isn't it the average of every point with respect to every other point? The distance of every point.
That is B, right? That is the B.
No. B is the average of the distance from every point in one cluster to every point in the next nearest cluster. A is the average of the distance of every point with every other point in the same cluster.
Same cluster. Okay. A is the average. Okay.
Yeah. So we only have to consider the nearest other cluster, is it? Not all the clusters.
Yeah, only the nearest cluster.
There is this question in graded assignment which asserts that poor initialization of centroids leads to poor convergence speed. This part was not covered in the lectures. Can you put some light on that, Sonim?
Yeah, sure. So, okay. So your point is poor choice of initial random centroids can affect the speed or the quality of clustering, or both?
No, all three. There are three. So all three were right. So it was talking about speed also as well as the actual output.
Okay.
Speed of convergence.
Speed and convergence. Okay. Give me a minute. I'll share my screen. So I'm going to take a very pathologically idiotic data set to prove this point. Okay. Okay, so imagine you have these data points. And they are actually symmetric. Okay. And by any chance, the random initialization takes the clusters on, the centroids are on this line.
On one side, yeah.
Yeah. On one line, which is kind of equidistant from both the groups. In that case, your clustering will not give you good answers.
It will never converge, right? It will never get to the...
Okay, what confused me was in the code, one of the points was taken as the centroid, not any random point on the plane.
Right. So that's right. I agree with you. There are different ways to initialize initialization in k-means clustering so that you get better results, and that is one of the methods. And so instead of choosing any random point on the input space, you can choose one of the data points as your initial centroids. That actually improves your clustering.
Sir, why wouldn't the clustering converge if both the centroids are on this line?
So, okay, again, imagine that this is your cluster. Sorry, not.
No, if you make them closer, right, and you take them to be in two different lines, right, the cluster itself will become different.
Sorry, I didn't get that. Okay, so imagine that this is a centroid chosen, and this is also a centroid chosen. Okay, so these two centroids are exactly they are sitting at exactly same distance from every point, and it's a mirror image. So this and this, they are same. Similarly, this oh no, I am making a mistake. Right, this one, and this one, they are same. Let me take some other color. This one, and this one. So your algorithm will be confused how to do this, right? Because all the data points, they basically belong to both the clusters. They are closest to the distance of any point. For example, this point.
So why can't the upper 4 be assigned to one class and the lower 4 be assigned to the
Right,
other?
right. My bad. Yeah. Let's say if you do this. So maybe I've taken a wrong example.
No. What if they are in the middle, right? Those two centroids are between, not outside the line, between the line. It will definitely get confused.
Sorry, align something like this.
No. Sorry.
Align something like this.
Suppose, yeah, draw a line. What if that centroids are just above and below the line?
Above right? And below the line.
And the intersection, right? Just above and below the intersection.
Okay, here and here.
So then they'll get confused, right?
Right. It will be confused.
I didn't get it. Why is that?
Let me think of another method of doing so. Again, I'll be taking a.
So this is the downfall. This is the problem with I think Euclidean distance, right? Because it only talks about the distance, not the direction of the distance.
Well, Euclidean distance, we can get rid of this problem, by the way.
So whenever we run into this problem of poor convergence, we can start with a different set of initial centroids, right?
Right. So if you look at the documentation of sklearn k-means algorithm and look at the code, there are slightly more sophisticated methods of initialization, not just taking any random points from input space. Give me 1 minute.
Okay.
Maybe. Right. Now I got the point. So imagine there is a line which is going exactly between these two sets. Okay, and this is a one centroid. This is one centroid, and this is another centroid. So what will happen is once you run k-means algorithm, what will happen is the first this centroid will jump to this place, and this centroid will jump to this place, and it will cluster as, okay, this is one cluster and this is another cluster. On the contrary, what should have happened is this should be one cluster, this should have been the other cluster. So yes.
Okay, so got it.
It is possible that your random initialization could mess up the quality of clustering. So sometimes you have, if you go only with random initialization from the input space, sometimes you have to perform the clustering multiple times.
Yeah, and then the speed is possible because, I can give an counter again an example. Like typically take that claim, no claim kind of a data, right? 90% is one cluster, 10% is another cluster. And even if you make 6-7 centroids, suppose you chose them all from the first cluster, right? Because the data is not weighted, it will take a long time to converge.
Right. That's a good example. Okay, so I hope Sandeep, I have answered the question.
Yeah, sure. Thank you.
Oh, yeah, thank you. So if there are no further questions,
Yeah,
Can we
I
start with week?
was hoping week 12 probably is the toughest week.
So you you will discuss that silhouette coefficient, right?
Yeah. Let's start with week 12 and then I'll answer.
Yes. Okay.
Yeah.
Hello, Karthik, you may start now.
Okay, I'll run through the slides, but I won't run through the entire thing. I'll skip several slides. So the core of neural networks is very similar to what we did in logistic regression, which is linear combination followed by nonlinearity. So that model we follow right through. So we don't want biology, no. So the basic idea of an artificial neuron is the same thing as I just mentioned. So you have something called the pre-activation, which accepts some activations as input, does a linear combination, which is basically W transpose X plus B kind of thing. So the pre-activation is this linear combination followed by some nonlinearity, which is G of Z. Okay, so that's the output. So the input is an activation, the output is an activation. In between, we have the pre-activations. That is one neuron. If you stack several neurons in a layer, and if you stack several of these layers together, you get a neural network. In this course, we are only focusing on feed-forward networks, right? So there are no backward connections. Everything moves from the input onward to the output. Okay, so we are looking at only regression and classification. Notation should be familiar to you by now. Data is also standard, n by m feature matrix and label vector for regression, and only change is label matrix for classification. So as a black box, what does a neural network do? You can just think about it as a function approximator, right? So it learns a function from the input space to the output space. So that is all it does. In the case of regression, it just predicts some real number, but for classification, it outputs a distribution, a categorical distribution over k classes. Okay, so for classification, there is one extra step. After the probability distribution, in inference, you just need to do this argmax over your k classes, right? So that is a small extra step compared to regression. So in regression, the h of x will give you the network's output, whereas in classification, for inference purposes, you need to do an argmax over h of x. So please stop me in between if something is not clear. Otherwise, I'll just keep going on. So there are three main components if you think about it. One is what is called the network architecture, right? So what are the different layers in your network? How many neurons are there in each layer, and what activation functions are there in a layer? And that is your network architecture, and then you have forward pass and then backward pass. Okay, so within a neural network, you have three components: the layers, weights and biases, activation functions. So layers, every neural network will have at least three layers, right? So this is a minimum: input, hidden, output. So if you remove the hidden layer, and if you just have input and output layer, then your model is essentially linear. So it will, if the output has a single neuron, then it's just a regression. It's just a linear regression model. If your output has multiple neurons and you are using softmax, then it would become a softmax regression. So you need at least one hidden layer with some non-linearity for this to be considered a proper neural network, right? So otherwise, there's no point of using a neural network. So three hidden layers, always remember that first is going to be input, last is output, and in between, whatever comes is a hidden layer. The number of hidden layers is a hyperparameter. So you could use 3 layers, 4 layers. If you use a large number of layers, then you have what is called a deep neural network. So yeah, so that is the layers. Okay, so layer 0 to layer capital L, right? So this is the notation we'll be following always. So this is important from the point of view of exam also. So layers are indexed from 0 to capital L. Okay, so 0 will be input, capital L will be output. And the number of neurons in each layer is again a hyperparameter, right? So the only thing which is fixed is S0 and S capital L. So S0 will be the number of input features and SL will be 1 or k depending on what type of problem you are actually solving. Everything else in between is variable, right? So you have to determine this by using a validation set, either cross validation, or you just look at the validation error and determine what these values should be. Okay, weights are nothing but the importance of the connections between successive layers in your network. Okay, so in this course, we are only having connections between successive layers. So we don't skip layers. It's always from L-1 to L. And this is what is the notation we'll be following. Where is that? WL, right? So I'm skipping a lot of slides because they're all quite obvious, right? So all the weights, if you put them together in a matrix, you have a weight matrix, right? So SL minus 1 cross SL is the dimensions of the weight matrix. So if you have a layer which has 3 neurons and the immediate layer after that has 2 neurons, then the weight matrix will be 3 by 2. Please note that it's not 2 by 3, right? So even though you could treat it as a 2 by 3 matrix, the convention that we are following is SL minus 1 cross SL. Okay, so what in that sense, what will Wij represent? It will represent the weight from neuron I in the previous layer to neuron J in the next layer. Okay, so that is what the weight matrix is. As far as biases are concerned, each neuron in a layer has a bias term associated with it. Okay, so note that this neural networks do not have this concept of dummy feature, right? So since we are using biases, we don't actually need the dummy feature. So it's whatever is the input feature vector, that will be the size of the input for a neural network. So this is also another point you need to remember. Okay, so this is a repeat slide, so I'm skipping this. Pre-activations get transformed into activations using an activation function. So this is the matrix form, right? So if in case you forget,
one small question.
Yeah, please.
We can call pre-activation as linear combination, right? We use the word in week 5, 6. Yeah.
Correct. Yeah, you are right. So it's just a fancy term for linear combinations. So the reason we stuck to pre-activations is that it is what happens just before applying the activation function. So you can call it the linear combination. So they are equivalent. Okay, so in case you forget the order of multiplication, right? Whether it should be A, W, or WA. One thing you can always remember is the shapes of the matrices, right? So your activations will always be of the form n cross number of neurons, right? N is the number of training examples or the batch size. SL will be the number of neurons, right? So this has to be of the form n cross SL. This has to be of the form n cross SL minus 1. So the only way to multiply these two matrices is AW plus B, right? So it can't be WA. So in case you forget this during exam or in future, try to recollect the shapes of these matrices. Okay, so that is one hint. Activation. So activation is applied element wise. That is another thing you need to note. So hidden layer activations are applied to each element of a matrix. Or if ZL is a vector, then it is applied to each element of the vector. Right. So why are activation functions required? If you remove activation functions, then it's just a cascade of matrix multiplications, right? So even if you have L layers, right, or how many ever layers you want, you can add. But if you are going to remove the nonlinear activation function, then it's just it degenerates into a linear model, right? So there is no use of having a neural network, right? So That's why we have nonlinear activation function. It's not just some activation function, it's a nonlinear function. Yeah, so there are three popular, what is most important in these three cases is the ranges, right? So try to recollect or commit this to memory roughly. I mean, for sigmoid, you also need to know the formula. For tan h, we don't expect you to know the formula, but just notice the range of tan h, right? It goes from -1 to 1. ReLU, of course, you need to know the formula because it's simple to remember, right? I am skipping this. You don't need to know vanishing gradients right now. You will deal with that in the next course in degree level. So you can skip that. Right. So there is a distinction between activation functions for the hidden layers and activation functions used at the output layer. For output layer, when it comes to regression, you typically use identity, right? And for classification, you use softmax. Okay, so for classification, you can also use sigmoid if you are doing binary classification. So we have not included it here, but you must know that it can be done. So it's not like if it is classification, I can use only sigmoid or only softmax. It depends on the use case, right? So you could potentially use sigmoid if you have a binary classification problem. So this is something you have to keep in mind.
So if I have added, let's say if I have added softmax and it happens to be a binary case, then it becomes the sigmoid function, right? Without me doing that explicitly. I think that's what my understanding is. That now?
Does it become the sigmoid? So I need to verify this, right? I'll get back to you on Discord. Just start a topic. It's a good question. I need to verify this. But yeah, the larger, so there are 2 points here, right? So if it is binary classification, you can still use softmax, that will work. But it's not necessary that you have to stick to softmax even in the case of binary classification, right? But I'll get back to you on this case where, yeah, that's a good point. Okay, so just start a thread on Discourse, we'll discuss that. Okay, so as for forward pass, see forward pass, we expect you to know the entire thing, right? Because it's very simple to remember this. You start at layer 0, or rather layer 1. Layer 0 is your input, right? So your activations are nothing but the feature matrix. And then for each layer, you compute iteratively the pre-activations or the linear combinations for that particular layer, followed by the non-linearity, right? So,
yeah, but where do we know the weights here?
So weights are what you need to learn.
Yeah, so that you will learn only while coming back, right? So that's why I had this question: how do we do the forward without knowing the weights?
So what happens is we if you look at, so forward pass is
that will be randomly initialized, right?
Yeah, it will be randomly initialized.
Bias.
Yeah, so I'm just trying to look at that particular slide. So let me just go here and see, this is a part of the learning algorithm, right? So you initialize the weights and then you do forward pass, loss, backward pass.
Okay.
Right. So when you initialize your weights, you'll have some weight vector.
Yeah, but how do you update the weights? The weights for the next layer? You have, with the initialization, you have W0.
Yeah, good point.
How do you get W1?
Yeah, good point. So you initialize the weight matrix for all layers at the beginning.
Oh, okay, good. Okay, thanks. I asked the question. So it is all okay. The entire matrix is initialized.
Yeah. So the all matrices are initialized. In fact, right. So if you have like one hidden layer and one output layer, right? So you have two weight matrices, one going from input to hidden, another one from hidden to output. So you initialize both the weight matrices at the beginning.
That's why we're using theta.
Yeah. So the theta, right? All parameters are initialized to start with. Okay, so that is one thing. And the second important point, I'll mention it while we come to backward pass. But for now, right? So this is the forward pass and it's computed iteratively. I hope there are no questions here. So see, this is the same algorithm. Only thing is that depending on what problem you're solving, the activation function and the output vector, output matrix will all change, right? But the skeleton of the algorithm is the same. Okay, so that's forward pass. Yeah, for regression, it's your squared error loss. It's the usual one. And for classification, it's the categorical cross entropy. Again, usual stuff. Yeah, so optimization is also familiar to all of us. It's gradient descent, and the whole idea is you need to find the gradient of the loss with respect to the weights and biases, right? So if you have even a moderately sized neural network will have several thousands of parameters. So you'll have to compute this gradient repeatedly. I mean, not repeatedly, but you have to compute this gradient for several values of weights and biases. So this is a pretty challenging problem. So back propagation is the algorithm that researchers have come up with to compute the gradients in one go, right? For all the parameters of your network. Right, so I won't go too much into back propagation now. I'll leave it to you to refer to the slides in case you haven't. So it's just repeated application of the chain rule. Okay, so it's chain rule all the way. So it's back propagation is actually a fancy way of saying that you apply chain rule to find the gradients. Okay, so the idea is you start with the gradients at the output layer. Once you have the gradients at the output layer, you use that. You piggyback on that to find the gradients at the hidden layer, right? And if there are multiple hidden layers, you just keep going back. So that is the reason it's called back propagation. The gradients are propagated backwards. Okay, so refer to this simple example for a very simple network. I am not going to go over this. In case anyone has any doubts, you can post this as a query in discourse, right? So for understanding the gradients in the case of a full-blown network, you need to know these three notations. So AL, ZL, and WL are familiar. This superscript G is nothing but the gradients of the loss with respect to all these terms, right? So that is what this notation stands for. And yeah, so these equations can be a bit tough. So what I would suggest is you can remember this one, these two, the next two, not so much. You don't need to exactly remember. But the trick to remembering these also is that you can always look at the shapes, right? So WLG will have the same shape as WL. And you can figure out which should be transpose of what and all this by looking at the shapes, right? But this first equation we expect you to know because it's quite simple, right? It's just chain rule applied to this particular equation, right? So Z is AW plus B. So gradient of Z is nothing but gradient of A into G prime of Z, right? So it's just chain rule again. Any questions here?
Yeah, there was a question on how many formulas. I gave an indirect reference to this part. If you want to comment directly also, it will be useful.
Yeah. Please remember this, but don't worry too much about the others.
Yeah, no, right? I said that without saying only remember that one. I said that remember the ones that you use for the programming questions.
Yeah. So I mean, I'll explicitly state that here. See, the point is not to remember the exact formula, right? Because in the end it will be very tough. So in reality, no one looks up. I mean, everyone looks up the formula for back propagation. In fact, no one does back propagation from scratch in the first place, right? So some library does it for them. So first equation we expect you to remember because it's very simple, and rest you can without feeling guilty, you can forget. Okay, I mean, temporarily at least.
Another question. Sorry.
And for both, G dash is basically Y minus Y cap.
So see,
right?
G dash
starting from the back, GL, G
yeah.
capital L dash is Y minus Y cap.
Yeah, so this gradient for the final layer is, as you said, it will be y predict minus y hat minus y. But for hidden layers, it will be different, right?
Yeah, no, that is also, I mean, for me, it's a network because that since that is simple and that is what I need to remember. So I'm
right,
just
yeah,
calculating
you
that
need to correct, yeah.
There is this question in quiz too. I'm sorry.
I just had one question. Do we need to know how to calculate the loss and the gradient test, meaning like numerically, because the element wise products is a little confusing.
You mean the matrix products?
Yeah. Like suppose there's one on slide 62. I think that's a gradient computation for classification.
Okay.
Okay, I don't know. Maybe it's a different slide. It just says gradient of the output layer. That's y hat. Yeah, this one, the classification part. So the previous
one. Okay.
Previous slide.
Okay.
Yeah, this one.
No. So see, this and all we don't expect you to remember because this terminology itself is like.
Yeah. Because the implementation is a little tough, I think. Like, and even in loss, like taking the log and then multiplying, we won't know which ones to multiply with which. That can get a little confusing.
Yeah.
So we don't need to do that.
You don't need to remember all this, right? So see, the idea you need to know is that backpropagation proceeds in this kind of a manner, and as long as that basic idea of the essence of backpropagation you must know. So see, if we give you one example, say one data point, and we ask you to do backpropagation, you must be able to do.
Okay, sure. One more question I had was, I think somewhere in one of the slides, it was mentioned that if there's no activation, then it just becomes a linear transformation. I had a question regarding the order of W. Actually, this was a question in quiz 1 also, where the question was which of the following is not a linear model, and the question given was W square X is equal to 0 or something like that. So I just wanted to understand, is that still linear or not linear? Am I missing something?
Okay, so I think when we say linearity, we mean linearity in the feature space, right? I mean, so you are linear with respect to the features.
No, actually, sorry, I thought the other way around, right? Because when it comes to polynomial, it was mentioned that even though it is x square and all the stuff, it's a linear in weights, and weights is what we are looking at. So it is still a linear model.
Oh, is it? Oh, okay. So
that's a specific comment saying that, note saying that even though it is x1 square, obviously polynomial, we do x1 square cube also, but the weight is still a linear term.
Okay, so see, it's okay, maybe the decision boundary is non-linear in the feature space, but in the transform space, it's linear. Yeah, I'm not sure. So this is something I need to check. I think we need to check on this one, because what is linear or linearity with respect to what is something I'm not very sure at this stage.
See, only when you are doing XW, right? XW is a linear equation. So
XW is linear,
yeah, whatever the X is. So this is in a linear form, but here after you do that XW, on top of that you are using that sigmoid, right? And there the non-linearities. Other than that, there is nowhere, correct? And that way you are like accumulating over multiple hidden units. So that means overall things like whatever you are getting is a complex like sigmoid of sigmoid of sigmoid, something like you are getting a very non-linear equation.
Yeah, so actually, Shreya, what is your question?
My question is then, I mean, I don't think those, I don't know if those questions will be there again, but in general, then would they be called linear or non-linear? Because I think I'm still confused. Like if there's a model called summation over all x w square x, will that be called linear or not? That is my question.
Okay, see, w square x for all I'm concerned is actually some w dash x, right?
Correct.
So it is linear, at least
it is linear, yes.
Yeah. So I would say, stick to, see, as long as you are linearly combining the features, I would still say that it's a linear model. And so even though this polynomial transform is in some sense linear in the transform feature space, right? But I won't say it's linear in the
original feature space.
Yeah, original feature space.
Okay. Okay, sure. Thanks.
Yeah. Okay. So coming back, yeah. So I think you know what to remember and what to skip momentarily for the exam. Until April 3rd, you can forget few things selectively. So activation function. Okay. So I'm skipping all this. We directly go to backward pass. So the only difference is that you start from layer capital L and go all the way back to layer 1. Okay. So G is identity for regression in the output layer. G is softmax and for classification. But I again stress on this, it's not always true that it has to be softmax. Okay, so that's backward pass. So once you have forward pass and backward pass, then you pretty much have all the ingredients that you need to define your algorithm. So this is the final algorithm for training a neural network. Initialize all your parameters, which we have called theta, do for each epoch, right? So this is standard gradient descent. So for each epoch, do a forward pass on the entire data, compute the loss. You have your true labels and your predictions, or rather your probabilities in this case. So compute the loss and do a backward pass using again the entire data and update your parameters, right? So this is important. This is a simultaneous update. Okay, so you don't do it for layer L and then you do it for layer L-1. No, it's you compute all the gradients at one go and then you update the parameters. Okay, so please note that what is iterative is only the computation of the gradients. The update of the gradients is not iterative. It's simultaneous. Yeah, so why
can you explain that again? We are doing the update also within the loop, right?
Yeah, we are doing the update also within the loop, but what I meant was that we are computing forward pass and backward pass layer by layer, right? So we do this for all the layers and update the weights just once for each epoch. That is what I meant. I mean, we don't update. So we don't do the backward pass for, say, the last layer and then update the weights. And then for layer L-1 and update the weights. So we do it for all layers and then update it once. Am I clear?
Okay. So number of epochs is the number of loops, but the layers are done at a shot.
Okay. See, once.
Yeah. Okay, I get it. It's a tough thing to visualize, but yeah.
Yeah.
See, only when you do the backward pass, you will come to know about the all DWs, right?
Right.
So you need to come all the way to the input. Like from X to Y, you have gone through forward pass. Now from Y to X, you need to come back. Then you have all the DWs.
Right.
Then you update all these things in one epoch.
Yeah. So just to add to that, in every epoch, you do one forward pass, one loss computation, one backward pass, and one update. So there are like E updates to the weight vector. E updates to all the parameters, right? So yeah. So we could do, see, this is standard gradient descent. We could do mini batch gradient descent also, which is typically advised because when you're dealing with neural networks, you'll have huge quantities of data. So you can't process all of that in one go. So typically you'll use a mini batch of say 20 or 30 and do the update. So this will turn into a nested loop. Okay, so that is all there is to it. So initialization, I'm skipping this because we are already like much beyond time. So yeah, so this overfitting is standard, right? In neural networks, very easy to blow up the parameter space. So we will end up overfitting. This architecture computation, I'm just deviating, this is something you must know, right? So how to compute the number of parameters given a layer, right? So if you're given a neural network, always remember that the first and last correspond to input and output layers. Everything in between is hidden layers, right? So yeah, so overfitting, how do we solve that? we can solve that using either the standard L1, L2 regularization by augmenting your loss function using some lambda regularization parameter, or there's something specific to neural networks which is dropout, or you could add more training data points, right? So which is standard across all models we have seen. Okay, so dropout, again, it's good to know. See, we didn't ask any question in the theory assignment also, so it's like good for you to know what dropout is. Yeah, so that is all. If there are any specific questions, we can go through them. If not, we can close, I believe.
Can you please
So there are
go
no.
through the...
Yeah, please. Two of you were.
Yeah, so I wanted to request you to, do one numerical for us. Maybe a small problem.
So small problem in the sense for.
So that at least if we could do it for 3 layers and see how forward pass and backward pass works.
Okay, so see, I'll quickly go over maybe the existing slides.
I hope we won't be asked to update weights and all by hand, right? I think it is going to be too tough for neural networks.
Yeah. So that is. See, typically, I mean, this will extend, I believe, to any example. If you understand how it's done for, say, one input, one hidden layer, and one output, right? So just one neuron. So you start with A0 equal to X, right? So X is your input, A0 will be your activation for layer 0, right? Which is the input. And then you just do the linear combination. So the weight connecting the input to the first hidden layer neuron is W1, right? So W1 A0 plus B1, right? So that is the linear combination, and the activation at layer 1 is G of that Z1, right? So this is what happens in layer 1. So output of layer 1 is A1. So you pass it to layer 2, it becomes W2 A1 plus B2, and then you do G of Z2, you get A2, right? So when you do A2, you have reached the end of your network, right? So your prediction y hat is nothing but A2. Okay, so once you have A2 or y hat, you can compute the loss. So I mean, you can substitute the numbers, I believe, right? But the standard protocol will be like this.
Right, and after we have got the loss.
Okay, after you have got that, you have to do the gradient computation. So gradient computation, what you do is you need these 4 values, right? The dou L by dou W1 B1, W2 B2, right? So what you do is you start from layer 2. Okay, so you start from layer 2. So dou L by dou W2, let's say, for example. So notice that this can be broken down into 3 parts, right? So y hat is nothing but A2. So you say it's dou L by dou A2 into dou A2 by dou Z2 into dou Z2 by dou W2, just the chain rule. Okay. So you do this, and then you do the substitution, right? It's y hat minus y.
Sir, I didn't get how you called it, the chain rule.
Okay, so see, L is the loss, right?
Yes, sir.
L depends only on y hat and y.
Yes.
Okay, so the first thing that you can differentiate L with is y hat. Okay, see, y is fixed because y is your true label, it's not a parameter here. So you do dou L by dou y hat. So I mean it's A2 because y hat is A2. So that first term you understand, right?
Yes, sir.
So once you have A2, then look at, so always keep going back and forth between your forward pass equations and your backward pass. So once you have the gradient with respect to A2, now you take, so what is variable here? The Z2, right? So if you change Z2, that's going to affect A2. So you do dou A2 by dou Z2. All right. That is, you continue the chain. So once I know Z2, the gradient with respect to Z2 depends on what? So Z2 could depend on 2 things. It could depend on, in fact, three things, right? It could depend on W2, A1, B2.
A1 and B2, right?
Right. So now we are interested in the partial derivative with respect to weight, W2. So we just include that. That is how we get the third term. So rest of it is just expansion, right? So
if the denominator was actually B2, then you would take a B2 in the last step.
exactly, yeah. You would just say it is dou Z2 by dou B2.
Right. Okay. Okay. Got it.
Okay, and then you just substitute the value. So dou A2 by dou Z2 is nothing but G prime of Z2, and dou Z2 by dou W2 is nothing but A1, right? So that's just chain rule again, and you keep doing this, right? So once you have with respect to W2, you need to compute with respect to W1. So if you notice, it's the same process. So W1 influences Z1, right? So you can go backwards also. W1 influences Z1. So it's W1 here, Z1 here. Z1 influences A1. So it's Z1 in the denominator, A1 in the numerator. A1 influences L, right? So that you get from layer 2 itself. So if you notice, there's the extra term, right? Dou L by dou A1, I'll get from layer 2. I'll plug that back into layer 1. This is the link in some sense between layer 2 and layer 1.
Okay, got it.
Okay, so any other questions?
I have a question, Karthik.
Yeah.
It was very well discussed in the lectures that why don't we initialize all the weights to 0 or some constant values, because we want them to evolve in different paths.
Right.
But we initialize them from a standard normal, and with high probability, if you take samples from a standard normal, you get values very close to 0. So my question is, would a uniform distribution away from 0 be a better choice of initializing the weights than the standard normal?
Okay, so see this, we just, we didn't even scratch the surface with respect to initialization, right? So there are, initialization in some sense is not a solved problem in neural networks. So there are plenty of initialization schemes, so to speak. So there is one thing called GLOROT, right? So GLOROT is one initialization scheme, I believe, which uses uniform distributions, and it also takes into account the number of neurons in each hidden layer, right? And so there are different initialization schemes, so to speak, right? And there is, I don't think there is any one scheme which is globally, good for every neural network to follow, right? But your question is, if we use
these two things are a little contradicting. We are initializing in a way that would ensure that the weights that are getting initialized is very close to 0, either side of 0, because it's being picked up from a standard normal distribution, and at the same time we are saying we shouldn't initialize the weights close to 0 or 0.
See, the point is, what we are saying is that you should not initialize all of them to be the same value, right? The same value could be 0, it could be 1, it could be any k, right? And that is different from saying that it's drawn from standard normal, right? Where the whole point is you have to make sure that you don't initialize them to the same value. It could be 0, it could be k, anything else.
Okay, I understand now. Even if there are very small differences between the weights initially, but because of chaos theory or something like that, the evolution would take completely different paths for different weights.
Exactly, yeah. All that we need is that there must be some difference in the weights.
Okay, thanks.
Okay, any other questions?
Maybe a silly question on the algorithm.
Yeah.
See, after the thing, we are finding the derivatives, right? The theta is a derivative.
Right.
After we find the derivatives, where is the inference part?
Yeah, so this is just the training part, right? So this algorithm is just for training the network and obtaining the weights. The inference part will be, for regression, it will just be plugging in X into your network and getting the output, right? So the final layer neuron will give you the regression target.
You see, here we are updating the gradients, right? We are not updating the weights as such. Or theta is the weight. Okay, theta is the weight everything is there. Yeah. Okay.
Yeah. So this is just a training algorithm, right? So only this is how you train the network. Inference will
you have to do a forward pass basically again.
Exactly. Yeah. You have to.
But with the calculated weights rather than the random weight. I mean, rather than the random weights.
Yeah, you are right. Yeah. Yeah, I think that is something we could have mentioned. Yeah, we missed it. So when inference also requires a forward pass. Yeah, but it requires only a forward pass. Yeah, that's a good point. Yeah, any other questions?
I don't know if I can ask actually, but how much in depth of the code do we need to know for the exam?
Much see code wise, it's just so forward pass and backward pass are straightforward, right? I mean, it's just the equations become. Oh, you mean you are asking for week 12 or like across
for week 12
weeks?
alone? No, for week 12 alone.
See, for week 12, this is just translation into NumPy, right? So it's just np dot transpose or a into at z, right? So that is all. So there is nothing to.
As long as I know how to read that, I should be okay.
Yeah.
Okay, thank you.
Okay, any other questions or shall we stop? Okay, so that's it from week 12. I think. Swarmin?
Yes. Thanks, Karthik. So, Rajiv or someone have any outstanding question from any of the weeks? We can answer them now.
One general question, if there is a dummy feature to be added, it will be clearly mentioned in the question, right?
Yes.
Okay, so no assumptions anywhere.
No.
Okay, thank you.
Any other question?
Yeah, will like regarding the quiz, sorry, this Entom, will it be like a kind of quiz too, or it will be even difficult than that?
So difficult in the sense, what do you mean by that?
Yeah, actually, even I also agree. Quiz 2 was quite a tricky one. So, and we haven't done, so well, myself, I can say that we haven't done well for the last, whatever the exams we have done. So, what kind of complexity or what kind of questions being asked? Like, should we follow only these questions, assignments questions will help us to do well?
See, the questions that we'll be facing in the Entom exam will definitely be coming from the same set of topics, and the practicing graded questions and practice assignments will help you. They might be asked in a not in a straightforward manner sometimes, just to check the understanding, as you saw in quiz 2. Okay, but the difficulty level will be very similar to quiz 2. Yeah.
Okay, anything about the distribution or like?
Yeah, so you can since an Entom exam, you can imagine that it will have questions covering the entire syllabus, but the major focus will be on the last 4 weeks because they have not been covered before. In any of the quizzes, I mean.
Okay. Mm-hmm.
Again, I cannot give you a percentage wise distribution or something like that, but I would suggest prepare for the entire syllabus. There will be questions from all weeks and all topics.
Mm-hmm.
Will there be a mix of topics? Like, I don't know if that's possible other than pre-processing, but.
When you say mix of topics, that means combining topics from different weeks into a single question?
Yeah.
Maybe, why not?
Yeah, okay. Okay, I get it. Fine.
on final thing, since I think we had discussed the soft vector, right, SVM. So if we have a question on vector, we are using the method that is used for the graded assignment, right? That sections.
Good question. So your question is, should we use that method or not, right?
So
Which method? That the WB calculation?
Yes.
That alphas method, please don't use. I mean, this inspection, right? I mean, just to clarify this, you can't find support vectors by inspection, right? So, and that is, let me just record it here also. Unless the data is like so simple, having like say 3-4 points, inspection cannot be done, right? So the output of SVMs is support vectors. We can't like use support vectors as input and some kind of back propagate and find the alphas.
Yeah, that is very tricky actually. Like
that was a question. I lost that entire 8 marks in that quiz. There was a quiz was a washout, big problem. So would we get similar things, and should we just take that approach? Which approach should we take?
So see this, I'll just comment alone I'll make, right? So whenever you're asked about, when you're given some kind of data and asked to find the support vectors, you can assume that it is soft hard margin SVMs, linearly separable data. Okay. And the only way you can, without any confusion, separate the data is by having, let's say, 2 support vectors at max, right? So more than that, it's very tough for you to find, right? So, and when you have 2 support vectors, I think what answer you wrote, right, that 1.25 by taking that vertical line, that seems fair enough, I would say, in general.
As far as the question of the examinations are concerned, if you can identify the 2 support vectors and you need to find W and B, so it's Wx1 plus B equal to 1 and Wx2 B equal to -1. From that you can find W.
Sorry, is someone speaking? It's not audible.
Yeah, what I'm saying is, as far as the questions of the examinations are concerned, if you can identify the support vectors and the things you are going to find out is W and B, then you can always get 2 equations like Wx1 plus B equal to 1 and Wx1 plus B equal to -1. From there you can find X and B without going to the alphas. That's a simpler way, in my opinion, for the questions in the examinations are concerned. Yeah, correct. Like those alphas are like pretty much confusing actually. Like what you said is correct. Like just creating those margins like Wx plus B and Wx plus B equal to +1 and -1. There is an additional information is that the difference between the 2 vectors is equal to 2 by the magnitude of W. From that you can find. We hardly can hear you actually. What I'm saying is there is an additional information.
Sandeep, somehow Karthik could hear you very well, but none of the others are able to hear you at all.
Okay, can you hear me now?
No, Sandeep, it's very, very low.
Please try actually, like let us try to find.
So what Sandeep was saying is that we also have this margin value 2 by norm W, and we can somehow use that to solve the equation. So see, in general, right, there's an update pending from our side. So we'll think Swarnim, Amrita and I will discuss and we'll get back to you on that. Right, Swarnim? Is that
right, Karthik? Yes. Okay.
I definitely want to, Srinivasan here, definitely want to thank the instructor team. I think we have asked quite a few questions, not just today, but through the course. And I think this has been probably the most, I said that for MLF, but I guess every time I say that, but definitely has been a very conceptually very challenging course, right? I think lots of concepts to learn. And I definitely like the way it has been approached, but I think it gives a very good, done well. I mean, if I have done better, it would have given me a better understanding. I still have to undo it. I plan to redo all the courses, all the lectures again, right, during April, and get a better understanding. But definitely want to thank the Intersective team for taking a lot of time to explain the concepts, explain the approach, and their help in solving issues. Thank you.
Yeah, I agree. I mean, thank you to the entire team. The live sessions and content, everything has been great.
Yeah, thank you. Thank you, everyone. We would like to make the experience, we tried hard. This was, and thank you that you appreciate our efforts.
And one suggestion I had, maybe I'll post it in Discourse also, but is it possible for alumni of that course to participate in future discourses? Because I tried doing it, I can't go to look at MLF discourse or whatever. I'm cut out from that. If I'm not taking the course, I can't participate in the discourse. But for MLT, is it possible?
It's visible for me. MLF is coming.
I might have done something wrong, so let me try it again. Yeah.
Okay, Srinivasan, we'll note it, and definitely discuss. So, is it that it is coming for some of the students it is accessible, for some it is not?
No, I might have not done it in the right way. So I'll check with Mukesh offline and then find out how he's able to access it.
No, I have not done anything. It's automatically listing. Maybe they have not blocked me.
No, we definitely didn't block Srinivasan. Okay. Any further questions?
No, I think that's all.
Right. Thank you, everyone. Yeah, it has been a very long session.
Yeah.
Okay. Thank you, everyone.
Okay.
Bye,
Thank
bye.
you, everyone. Bye.
All the best for your exams.
Yeah. Thank you.
Thank you.
Thank you, sir.
Thank you.
Yeah, thank you so much.
Bye then.